Hello there and welcome back to the Science Sleepy Minds. You're floating in the silent dark, wrapped in your blanket cocoon, and above you, or below you, directions don't really matter out here. The universe stretches in every direction, a tapestry of galaxies spinning through the void like dandelion seeds caught in an eternal wind. For decades, astronomers measured this cosmic ocean with tools that could barely pierce the surface, mapping what they thought was the full extent of everything. Then the James Webb Space Telescope opened its golden eyes, and the universe whispered a secret. You had no idea how big I really am. Every textbook measurement, every confident declaration about the observable universe's boundaries, JWST just crumpled them like yesterday's grocery list. You probably won't survive the existential vertigo of realizing that what we called the edge was just the limit of our instruments, not reality itself. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Drop a comment telling me where you're listening from and what time it is in your corner of the world. I love seeing how this little community spans continents and time zones. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're standing at the threshold of a revolution that's unfolding right now, in 2024 and into 2025, as JWST beams down data that's rewriting cosmology faster than scientists can publish papers. The Hubble Space Telescope, bless its aging circuits, spent 3 decades becoming humanity's most famous eye in the sky. It showed us galaxies billions of light years away, captured the deepest field images ever taken, and convinced us we had a pretty solid handle on the universe's size. Mainstream science settled on a comfortable number. The observable universe stretches about 93 billion light-years across, accounting for expansion since the Big Bang roughly 13.8 billion years ago. Neat, tidy, confidence-inspiring. But here's the thing about confidence in science. It's always one better telescope away from humility. JWST launched on Christmas Day 2021, a $10 billion gamble wrapped in a sunshield the size of a tennis court, parking itself 1 million miles from Earth at a gravitational sweet spot called Lagrange Point 2. Unlike Hubble, which sees primarily invisible and ultraviolet light, JWST peers into the infrared spectrum, detecting heat signatures from objects so distant and ancient that their light is stretched into wavelengths invisible to human eyes. It's like upgrading from a magnifying glass to a thermal camera. You're not just seeing more, you're seeing differently. The first deep field images dropped in July 2022, and the astronomical community collectively lost its composure. Galaxies that Hubble rendered as faint smudges appeared as crisp spirals and bars in JWST's vision. But the real shock came when researchers started calculating distances. Objects that should have been at the theoretical limit of detection, galaxies born when the universe was a mere infant, weren't just visible, they were everywhere, crowding the ancient cosmos like commuters on a rush-hour train. Historians of science will mark this as the moment when our cosmic census had to be torn up and restarted. Remember when scientists thought the early universe was a simple place? A hot, dense soup cooling into hydrogen atoms, those atoms clumping into the first stars over hundreds of millions of years, those stars gathering into the first primitive galaxies. A nice linear story. JWST said, "That's adorable, but no." The telescope revealed fully formed galaxies, massive, structured, impossibly organized, existing just 300 to 500 million years after the Big Bang. That's not enough time. The math doesn't work. It's like finding a skyscraper in a neighborhood where construction permits were only issued last Tuesday. One quirky detail that makes this even stranger. Some of these ancient galaxies appear brighter than they should be, given their age and distance. Astrophysicists are still arguing whether this means stars formed more efficiently back then, or if we're fundamentally misunderstanding how light behaves over cosmic timescales. Or, and this is the fringe camp, if something about the universe's early expansion was radically different than current models predict. It's the kind of puzzle that gives theorists stress streams and graduate students dissertation topics for a decade. You sink deeper into your pillow, and maybe you're wondering, what does bigger even mean when we're talking about the universe? The observable universe is defined by how far light has travelled since the Big Bang, but JWST's discoveries aren't adding physical space. They're revealing that our measurements of existing space were wrong. The universe didn't suddenly inflate. We suddenly got better glasses. Those galaxies were always there, calmly existing billions of light years beyond what Hubble could detect, waiting for instruments sensitive enough to catch their faint, ancient whispers. The implications ripple outward like stones dropped in a pond. If the early universe was more crowded and structured than we thought, then our models of cosmic evolution, how matter clumped, how dark matter behaved, how the first black holes formed, all need revisions. The comfortable narrative taught in every cosmology class is now marked with asterisks and footnotes, and this is just section 1. We haven't even gotten to the part where galaxies that shouldn't exist challenge the laws of physics, or where the universe's expansion rate produces contradictory answers depending on how you measure it. But that's for later, when your eyelids are heavier and the room has dissolved into that pleasant weightlessness before sleep truly claims you. You're drifting now through the cosmic timeline, rewinding past civilizations and ice ages, past the formation of Earth, past the birth of our sun, past entire generations of stars that lived and died before our solar system even began condensing from interstellar dust. You keep rewinding, faster, through epochs where the universe was unrecognizable, hotter, denser, simpler. 13 billion years fall away like pages torn from a calendar, and suddenly you're hovering in the infant cosmos just 300 million years after the Big Bang. The textbooks told you this era should be dark, nearly empty, a transitional phase between the primordial fireball and the first glimmers of starlight. The textbooks lied. JWST's infrared detectors locked onto something that shouldn't be there. Galaxies. Not tentative little proto-galaxies, not scattered clumps of gas struggling to ignite their first stars, but full-fledged galaxies, mature and structured, blazing with the light of millions of suns. These are the 13 billion year ghosts, cosmic apparitions that haunt every model of early universe development. One particularly troublesome example, catalogued as Glass Z13, appears to have formed when the universe was only 300 million years old. To put that in perspective, if the universe's current age were compressed into a single year, Glass 13 would be celebrating its birthday on January 8th. That's absurdly early for a galaxy to have assembled itself. The mainstream historical context makes this even more shocking. For decades, the standard cosmological model called Lambda CDM, which sounds like a failed boy band but is actually the framework describing the universe's composition and evolution, predicted a dark age lasting several hundred million years after the Big Bang. During this period, the universe was supposedly filled with neutral hydrogen gas, opaque to visible light, slowly cooling and clumping under gravity's patient pull. The first stars, population 3 stars made of pure hydrogen and helium, were expected to ignite around 100 to 200 million years post-Big Bang. Those stars would then gather into the first dwarf galaxies over the next few hundred million years, like pioneers building frontier towns. It was a gradual process, or so everyone thought. JWST just revealed that the universe apparently skipped several chapters of this story. Not only do galaxies appear earlier than predicted, but they appear mature, with disk structures, spiral arms in some cases, and evidence of multiple generations of star formation already complete. It's the astronomical equivalent of carbon dating what you think is an ancient campfire site, and discovering it contains plastic water bottles. The timeline is wrong, which means either our understanding of how galaxies form is wrong, or our understanding of the early universe's conditions is wrong, or, and this keeps cosmologists awake at night, both are wrong. Here's a quirky detail that doesn't make it into most news coverage. Some of these ultra-distant galaxies show spectral signatures indicating the presence of heavy elements like oxygen and carbon. These elements don't exist naturally. They're forged inside stars through nuclear fusion and scattered into space when those stars explode. Finding heavy elements in galaxies that formed only 300 million years after the Big Bang means that an entire generation of massive stars must have been born, lived their brief violent lives, and died as supernovae even earlier, perhaps within the first 150 to 200 million years. That compresses the timeline so aggressively that it borders on absurd. Stars need time to form, fuse elements, explode, and have their debris recycled into new stars. You can't rush nuclear physics, yet somehow the early universe managed exactly that. Historians of astronomy will note that this isn't the first time distant observations overturned comfortable theories. In the 1990s, Hubble's deep field images revealed galaxies far more numerous and distant than expected, forcing revisions to models of cosmic structure formation. But those were tweaks, refinements, adjusting knobs on a machine that still fundamentally worked. JWST's discoveries feel more like discovering the machine has extra gears nobody knew existed. The difference in scale and implication is profound. Scholars still argue whether these early galaxies formed through top-down processes, where large structures fragmented into smaller ones, or bottom-up processes, where small dwarf galaxies merged into larger systems. The Lambda CDM model strongly favours bottom-up assembly, supported by decades of simulations and observations. But the JWST ghosts don't seem to care about our preferences. They're just there, fully formed, challenging us to explain how bottom-up assembly could work so efficiently in the chaotic early universe. Some researchers are now proposing that dark matter, the invisible scaffolding that makes up most of the universe's mass, behaved differently in the first few 100 million years, clumping more aggressively than current models allow. Others suggest that the initial density fluctuations from the Big Bang were stronger than we thought, giving gravity a head start on galaxy construction. Then there's the fringe camp, the researchers who whisper at conferences after a few drinks. What if the Big Bang wasn't the absolute beginning? What if these impossibly early galaxies are actually remnants or echoes from a previous cosmic cycle, or from adjacent regions in a larger multiverse structure? It's speculative, bordering on philosophical, but JWST's data is forcing mainstream cosmology to at least glance toward ideas it previously dismissed. When your observations break your best theories, you have to consider uncomfortable possibilities. You pull your blanket tighter, feeling the weight of cosmic time pressing down like a physical thing. Those galaxies, those 13 billion-year ghosts, have been broadcasting their light across the universe since before Earth existed, before the Milky Way took its current shape, before anything familiar had even begun. Their photons travelled through expanding space for eons, stretching from visible light into infrared wavelengths, waiting for a telescope sensitive enough to catch them. And now we have that telescope, and it's telling us the universe's baby pictures look nothing like we expected. The infant cosmos was apparently precocious, assembling galaxies with the efficiency of a master architect while we assumed it was still learning to stack blocks. Sweet dreams are made of existential recalibrations. You're lying there, eyes closed, and maybe you're wondering how we even know how far away these ghostly galaxies are. After all, space doesn't come with mile markers, and you can't exactly pull out a cosmic tape measure when you're dealing with objects billions of light years distant. The answer lies in one of the universe's most elegant tricks, redshift, the stretching of light that turns distant galaxies into time machines. JWST's entire design revolves around exploiting this phenomenon, and understanding redshift is like getting the decoder ring for the universe's secrets. It's simpler than it sounds. Promise. Perfect material for your drowsy brain to process while reality softens around the edges. Light behaves like a wave, rippling through space with a specific wavelength that determines its colour. Blue light has short, tight waves. Red light has longer, lazier waves. When a light source moves away from you, those waves stretch out, shifting toward the red end of the spectrum. You've experienced the audio version of this if you've ever heard an ambulance siren change pitch as it passes. The sound waves compress as it approaches, higher pitch, and stretch as it recedes, lower pitch. That's the Doppler effect, and light does the same thing. An object racing away from you will have its light redshifted. One approaching will be blue shifted. Now here's where it gets cosmically beautiful. The universe itself is expanding, carrying galaxies away from each other like raisins in rising bread dough. The farther away a galaxy is, the faster space expands between us and it, and the more its light gets stretched during its journey to our telescopes. A galaxy 1 billion light-years away has its light mildly redshifted. A galaxy 10 billion light-years away has its light dramatically redshifted, with ultraviolet and visible wavelengths stretched all the way into the infrared spectrum. The most distant galaxies JWST detects have redshifts so extreme that light originally emitted as energetic ultraviolet radiation arrives as lazy mid-infrared heat, invisible to Hubble's sensors, perfectly tuned to JWST's detectors. Astronomers quantify this with a number called Z, the redshift parameter. A galaxy with Z equals 1 has had its wavelengths doubled during its light's journey. The galaxy Glass Z13 we mentioned earlier, it has a redshift around Z equals 13, meaning its wavelengths have been stretched to 14 times their original length. That corresponds to a look-back time of about 13.5 billion years, placing it just 300 million years after the Big Bang. Every increase in redshift is a step further back in cosmic history, and JWST is designed to push that frontier to Z equals 20 or beyond, epochs so early that no previous telescope could reach them. The mainstream historical milestone here is Hubble's 1929 discovery that the universe is expanding at all. Edwin Hubble, the man not the telescope, measured the redshifts of nearby galaxies and noticed a pattern. The farther away they were, the faster they receded. This linear relationship, now called Hubble's law, was the first observational evidence that the universe had a beginning, that it wasn't static and eternal as many scientists, including Einstein, had assumed. The expansion meant you could rewind the cosmic clock to a point where everything was compressed into an infinitely dense state, the Big Bang. Redshift transformed from a curious optical phenomenon into the Rosetta Stone for cosmic history. But here's a quirky complication that doesn't always make it into the popular explanations. Cosmological redshift isn't quite the same as Doppler shift, even though they look similar. Doppler shift happens because an object is moving through space. Cosmological redshift happens because space itself is stretching, carrying galaxies along for the ride while simultaneously stretching the light waves travelling between them. It's a subtle distinction, like the difference between a taxi driving you across a city versus the city expanding while you sit still, but it matters when you're calculating distances at cosmic scales. The math gets complicated, involving general relativity and the universe's expansion history, which is why astronomers use redshift as a convenient proxy for distance, rather than trying to convert everything into light years. JWST's infrared vision is specifically engineered to catch heavily redshifted light. Its primary mirror, that gorgeous 18-segment gold-plated hexagon, is optimized for wavelengths between 0.6 and 28.5 microns, far beyond what human eyes can see. Gold coating isn't just for looks. Gold reflects infrared light more efficiently than aluminum, squeezing every precious photon out of the universe's faintest whispers. The telescope's instruments, NIRCam, near-infrared camera, NIRSpec, near-infrared spectrograph, MIRI, mid-infrared instrument, and others, work together to not just image distant galaxies but analyze their light, breaking it into spectra that reveal composition, temperature, motion, and age. scholars still argue about the precise relationship between redshift and distance at extreme values. The universe's expansion rate isn't constant. It's accelerated by dark energy, slowed by matter's gravity, and varied over cosmic history in ways we're still mapping. So converting a redshift measurement into an actual distance requires assumptions about the universe's composition and evolution. Get those assumptions wrong, and your distance estimates shift by hundreds of millions of light years. This is partly why JWST's early galaxy discoveries are so controversial. They're not just finding distant objects, they're revealing that our expansion models might need serious revision, which we'll get to when your breathing has slowed and the room has gone properly dark. There's also a fringe debate about whether redshift always means distance. A tiny minority of astronomers have proposed intrinsic redshift theories, suggesting that some redshift could be caused by objects' intrinsic properties rather than cosmic expansion. Mainstream science has thoroughly debunked these ideas through multiple independent lines of evidence, but the debates flare up occasionally in obscure journals, usually accompanied by eye-rolling from the cosmology establishment. It's the astronomical equivalent of flat Earth theories, not worth serious consideration, but persistent enough to warrant occasional footnotes. You shift position, your mind floating on these concepts like a leaf on a stream. Every ancient galaxy in JWST's images is a message written in stretched light, each redshift value a timestamp from the universe's childhood. The telescope doesn't see galaxies as they are now, it sees them as they were, billions of years ago, frozen in time at the moment their light began its long journey. Some of those galaxies probably don't even exist anymore, having merged with others or dispersed into intergalactic space. You're looking at ghosts twice over, distant in both space and time, phantoms from an era when the cosmos was unrecognizable, captured only because JWST can decode the red-shifted whispers they left behind. The universe keeps its secrets in the language of stretched light, and we finally built a translator good enough to read the oldest messages. You're floating in that comfortable space between waking and sleep, where abstract concepts feel more like physical sensations than intellectual exercises, and this is the perfect state of mind for contemplating how spectacularly broken our understanding of the universe's expansion has become. There's a problem in cosmology so frustrating, so mathematically stubborn, that it's earned its own dramatic name, the Hubble Tension. It sounds like a thriller novel, but it's actually the increasingly awkward fact that when scientists measure how fast the universe is expanding, they get different answers depending on which method they use. And JWST, rather than solving this problem like everyone hoped, has made it significantly worse. The universe's expansion rate is quantified by something called the Hubble constant, usually written as H0, H0, which describes how fast space is stretching at the current cosmic moment. For decades, astronomers used two primary methods to measure this value. The first method looks at the early universe, specifically the cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space. Satellites like the Planck mission measured the CMB's temperature fluctuations with exquisite precision, then used our best cosmological models to calculate how fast the universe must be expanding today to produce the patterns we observe. This method consistently yields a Hubble constant around 67 kilometers per second per megaparsec. Don't worry about the units, just know it's a specific number. The second method looks at the nearby universe, measuring distances to galaxies using standard candles, objects with known intrinsic brightness, like certain types of exploding stars called Type 1 supernovae. By comparing how bright these objects appear versus how bright they should be, astronomers calculate distance, combine those distances with redshift measurements of how fast galaxies are receding, and you can work out the current expansion rate. This method, refined extensively by astronomer Adam Rees and others, consistently yields a Hubble constant around 73 kilometers per second per megaparsec. You see the problem? 67 versus 73. That's roughly a 9% difference. which might not sound catastrophic until you realise that both measurements are incredibly precise, with error bars so small they shouldn't overlap at all. In mainstream science, when two high-precision measurements of the same quantity disagree, something is deeply wrong. Either one method has a subtle, systematic error nobody's identified, or, more excitingly and terrifyingly, our fundamental models of cosmic evolution are missing something crucial. The historical context here is important. Until about 15 years ago, measurements of the Hubble constant were messy enough that uncertainties easily accommodated discrepancies. Different teams got values ranging from 50 to 90, and everyone shrugged and said we needed better data. But as instruments improved and error bars tightened, instead of converging on a single value, the two methods diverged into distinct camps, each confident in their measurements, each unable to find flaws in the other's methodology. It's like two groups of surveyors measuring the same mountain from different sides and getting heights that differ by hundreds of feet, both using calibrated equipment, both following proper procedures, yet arriving at incompatible answers. Enter JWST, stage left, carrying everyone's hopes that its unprecedented sensitivity would resolve the tension. Maybe it would reveal subtle errors in distance measurements to nearby galaxies, or uncover unexpected populations of objects that skewed the early universe calculations. Instead, JWST's first years of operation have generally supported the higher value around 73, confirming the measurements from the nearby universe method while making the discrepancy with the early universe method even more statistically significant. Some recent JWST observations have pushed the tension beyond 5 sigma, the gold standard in physics for declaring something is genuinely anomalous rather than a statistical fluke. Here's a quirky detail that makes this more unsettling. The Hubble tension isn't just an academic disagreement about decimal places. The expansion rate determines fundamental things like the universe's age. If H0 is 67, the universe is about 13.8 billion years old. If H0 is 73, the universe is closer to 12.8 billion years old. That's a billion-year discrepancy, and when JWST finds galaxies that appear fully mature at cosmic ages of 13.5 billion years, the timing becomes even more problematic. An older universe gives those early galaxies a bit more breathing room. A younger universe makes their existence even more impossible to explain. The tension propagates through every cosmological calculation like a crack spreading through ice. Scholars still argue about what the Hubble tension means. The conservative interpretation is that there's a subtle measurement error lurking somewhere, perhaps in how we calibrate Cepheid variable stars, another type of standard candle, or in how we model the physics of Type 1a supernovae, or in assumptions about dust extinction dimming distant objects. Dozens of papers propose tweaks and corrections, but none have successfully reconciled the values. The moderate interpretation suggests we're missing something about the universe's composition. Maybe dark energy isn't constant over time, or maybe there's an unknown particle or field affecting expansion in ways our models don't capture. Then there's the radical interpretation, whispered in the back rows of conferences. Maybe general relativity itself needs modification at cosmological scales. Einstein's equations have passed every test thrown at them for over a century, but they've never been rigorously tested at the scales of galaxy clusters and beyond. Perhaps gravity behaves slightly differently across billions of light years than it does in our solar system. Modified gravity theories like MOND, modified Newtonian dynamics, have been proposed to explain galaxy rotation curves without invoking dark matter, and some researchers wonder if similar modifications could resolve the Hubble tension. Mainstream cosmology treats these ideas with deep skepticism. You don't casually overturn Einstein without extraordinary evidence, but the inability to resolve the tension through conventional means is slowly making radical options less radical. JWST's contribution to this mess is providing more precise measurements of distances to galaxies, better characterizations of standard candles, and deeper observations of the early universe's structure. Every improvement in data quality should, in theory, narrow the uncertainty and point toward a resolution. Instead, it's sharpening the contradiction, making it clearer that this isn't a measurement error but a genuine crisis in our understanding. The math is breaking down, and somewhere in the equations describing cosmic expansion, there's either a missing term or a wrong assumption, and nobody's quite sure which. You sink deeper into your pillow, contemplating a universe that can't agree on how fast it's expanding, like a car with two speedometers showing different values. The comfortable certainty of cosmology, the sense that we had the universe's story basically figured out, has given way to a more honest uncertainty. JWST was supposed to be the instrument that answered lingering questions. Instead, it's revealing that some of our most fundamental measurements might be built on shaky foundations, and the universe is considerably stranger than the models predicted. The tension remains unresolved, a mathematical knot nobody can untie, tightening with every new observation. You're drifting through the cosmic nursery now, that epoch when the universe was barely out of its infancy, and you're about to encounter something that makes astrophysicists rub their temples in frustration. Galaxies that grew up way too fast. Imagine finding a 6-month-old baby who's already walking, talking in complete sentences, and expressing strong opinions about fiscal policy. That's essentially what JWST has discovered scattered across the early universe. Massive structured galaxies that shouldn't exist yet. Cosmic overachievers that violate every timeline we thought we understood about how matter assembles itself into organized systems. The standard model of galaxy formation is actually quite elegant when you lay it out. After the Big Bang, the universe was nearly uniform, just hydrogen and helium gas with tiny density variations. Quantum fluctuations stretched to cosmic scales during inflation. Dark matter, unaffected by radiation pressure, began clumping first, creating gravitational wells that attracted normal matter. Gas fell into these wells, compressed, heated, and eventually ignited the first stars. Those stars grouped into small dwarf galaxies, which merged over hundreds of millions of years into progressively larger systems. It's hierarchical assembly, bottom-up construction, like building a city starting with individual houses that gradually cluster into neighborhoods, then districts, then a metropolitan area. The process should take time, lots of time. JWST looked at the universe when it was 500 to 700 million years old and found galaxies with stellar masses equivalent to 10 billion suns or more. These aren't tentative little proto-galaxies. They're massive systems that, according to our models, require several billion years of steady star formation to construct. It's like carbon dating a medieval cathedral and discovering it was built in 3 weeks. The timeline simply doesn't accommodate the amount of stellar mass observed. Even if star formation occurred at the absolute maximum efficiency, converting nearly all available gas into stars, which never happens, you still can't pack enough time into those early epochs to build galaxies this large. One particularly troublesome example is a galaxy dubbed CEERS-93316, initially thought to have a redshift around Z equals 16, placing it just 250 million years after the Big Bang. Subsequent analysis revised this to a somewhat less extreme but still shocking Z equals 4.9, but the pattern holds across multiple discoveries, massive galaxies appearing far earlier than simulations predict. Computer models of galaxy formation, running on supercomputers for months at a time, simulate how dark matter halos grow and capture gas, how stars form and explode, how galaxies merge and evolve. These simulations, calibrated against decades of observations, consistently show that billion solar mass galaxies shouldn't appear until the universe is at least 1 to 2 billion years old. JWST found them at half that age or less. The mainstream scientific response has been a flurry of paper revisions and model adjustments. Maybe star formation efficiency in the early universe was dramatically higher than we assumed, perhaps because gas was denser, or metal-poor stars formed more readily, or feedback mechanisms, like supernova-driven winds that blow gas out of galaxies, were weaker. These adjustments can squeeze a bit more mass into earlier epochs, but they're band-aids on a structural problem. You can tweak parameters only so much before you're essentially admitting the model's foundation is cracked. Here's a quirky detail that deepens the mystery. Some of these early massive galaxies show evidence of already having old stellar populations. Stars have lifespans inversely proportional to their mass. The biggest, brightest stars burn out in just a few million years, while smaller stars can smoulder for billions. When astronomers analyze the light spectra from these early galaxies, they detect signatures of red, older stars mixed with young blue ones. That means these galaxies had already experienced multiple generations of star formation, with enough time for massive stars to be born, live, die, and have their debris recycled into new stars. You're looking at galaxies with history, with age, existing when the universe itself barely had a history. Scholars still argue about whether these observations represent a crisis or just a course correction. The optimistic camp says galaxy formation is just more efficient than we thought, and models will be updated to reflect the new data, science working as intended. The pessimistic camp points out that every adjustment to make early galaxy formation faster creates new problems elsewhere, like overproducing galaxies in the later universe, or requiring dark matter to behave in ways that conflict with other observations. It's like fixing a leak in your ceiling and discovering that doing so causes your basement to flood. There's also a measurement concern worth mentioning. Determining a galaxy's stellar mass from its light is tricky. You have to account for dust that absorbs and re-emits starlight, for the galaxy's star formation history, for the types of stars present. Early JWST results relied on photometric measurements, essentially educated guesses based on how bright the galaxy appears in different infrared filters. More precise spectroscopic follow-up observations have sometimes revised initial mass estimates downward, making some galaxies less massive than first thought. But even with conservative estimates, the fundamental problem persists. Too much mass, too early. Then there's the fringe speculation that maybe, just maybe, these aren't galaxies in the conventional sense. What if some of these ultra-massive objects are primordial structures formed through different mechanisms, perhaps direct collapse of gas clouds into supermassive black holes that then accumulated stellar envelopes or remnants of cosmic strings, hypothetical one-dimensional defects in space-time left over from the Big Bang, or even artifacts of a pre-Big Bang cosmology where matter existed in some form before our universe's clock started ticking. These ideas live on the edges of respectability, mostly because they're unfalsifiable with current data, but the fact that they're being discussed at all indicates how genuinely puzzling these observations are. You pull the covers up to your chin, your mind swirling with images of galaxies assembling themselves at impossible speeds, like time-lapse footage running at triple speed. The universe's adolescence was apparently far more eventful than anyone predicted, a period of frantic growth and assembly that our leisurely models never anticipated. JWST has given us a window into cosmic puberty, and it turns out the universe hit its growth spurt way ahead of schedule, leaving theorists scrambling to explain how physics could work fast enough to accommodate what we're seeing. Somewhere in the equations governing gravity, gas dynamics, and star formation, there's a missing piece, a factor or process that accelerates galaxy assembly in the early universe. We just haven't found it yet, and every new JWST observation is another reminder that the cosmos doesn't care about our carefully constructed timelines. The galaxies grew too fast, and the universe isn't telling us how it pulled off the trick. You're settling deeper into sleep's embrace, and now we need to talk about the universe's most pervasive mystery, dark energy, that invisible force pushing space apart at an accelerating rate, accounting for roughly 68% of everything that exists. For over 2 decades, cosmologists treated dark energy as a constant, an unchanging property of space itself, often represented by Einstein's cosmological constant. the Greek letter lambda. It was weird, sure, but at least it was consistently weird, predictable in its behaviour. Then JWST started gathering data on distant supernovae and ancient galaxies, and the evidence is beginning to whisper something unsettling. Dark energy might not be constant after all. It might be changing, evolving, growing stronger or weaker over cosmic time, and if that's true, Einstein's cosmological model is in serious trouble. The story of dark energy begins with a shock in 1998, when two independent teams studying distant Type 1, a supernovae, discovered that the universe's expansion isn't slowing down under gravity's pull, it's speeding up. This was the astronomical equivalent of throwing a ball in the air and watching it accelerate upward instead of falling back down. Something was counteracting gravity on cosmic scales, pushing galaxies apart with increasing vigour. The discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics, and it fundamentally rewrote our understanding of the universe's fate. Instead of eventually collapsing back on itself or coasting to a stop, the universe would expand forever, accelerating into a cold, dark, diluted eternity. The simplest explanation for dark energy is Einstein's cosmological constant, which he originally introduced in 1917 to keep the universe static, back when everyone thought it wasn't expanding, then famously abandoned as his biggest blunder after Hubble discovered cosmic expansion. The cosmological constant represents energy inherent to space itself, vacuum energy, springing from quantum fluctuations. It doesn't dilute as space expands. Instead, as the universe grows, more space means more dark energy, which drives faster expansion in a runaway feedback loop. Mathematically, it's represented by the parameter W, omega, which equals exactly -1 for a true cosmological constant. Everything in the lambda CDM model assumes W equals -1, a fixed value for all time. But JWST's observations of high redshift supernovae and the distribution of early galaxies are producing data that hints W might not be exactly -1. Some analyses suggest it could be closer to -0.8 or even -0.7, and more provocatively, that it might vary with cosmic time, a scenario called quintessence, where dark energy is a dynamic field rather than a static property of space. The evidence isn't conclusive yet, but the direction is consistent. Multiple independent measurements are leaning toward a dark energy that changes, that was perhaps weaker in the early universe, and has grown stronger over billions of years. Here's why this matters enormously. The lambda CDM model is the foundation of modern cosmology. It successfully explains the cosmic microwave background's temperature fluctuations, the large-scale structure of galaxy clusters, the abundances of light elements forged in the Big Bang, and countless other observations. It's been tested and validated more thoroughly than almost any scientific model in history. But it's built on the assumption that dark energy is constant. If W deviates from -1, especially if it changes over time, then lambda CDM isn't wrong exactly. It's incomplete. The model would need a new component, a new field or force that we haven't identified, and all the predictions about the universe's past and future would need recalculation. A quirky detail that cosmologists find particularly maddening. Quantum field theory predicts that vacuum energy should exist, but when you calculate how much there should be based on known physics, you get an answer that's wrong by a factor of 10 to the power of 120. That's not a typo. 120 orders of magnitude, the worst prediction in the history of physics. The observed dark energy density is incredibly tiny compared to theoretical expectations, so small that it seems suspiciously fine-tuned. Some researchers see this as evidence that we fundamentally misunderstand vacuum energy, and that dark energy might be something else entirely, a scalar field, extra dimensions leaking energy into our universe, or a modification to general relativity at cosmic scales. scholars still argue fiercely about what JWST's data actually shows. Measuring W requires incredibly precise distance measurements to high redshift supernovae, and systematic errors can masquerade as evidence for evolving dark energy, dust extinction, gravitational lensing, supernova evolution over cosmic time. All these factors can bias results if not properly accounted for. The conservative position is that current data is still consistent with W equals -1 within uncertainties, and apparent deviations will disappear with better calibration. The moderate position acknowledges that the hints of variation are intriguing and warrant further investigation with larger samples. The radical position says we're seeing the first cracks in lambda CDM, and within a decade we'll have undeniable proof that dark energy evolves. There's also the fringe theory that dark energy doesn't exist at all, and that what we're interpreting as accelerated expansion is actually evidence that we're living in a giant underdense void, a region of space with lower than average matter density. Light travelling through this void would appear red-shifted in ways that mimic accelerating expansion. Mainstream cosmology has mostly ruled this out through multiple independent observations, but the idea still surfaces in niche journals, usually accompanied by elaborate explanations for why it's being suppressed by the establishment. If dark energy is indeed changing, the implications ripple through every aspect of cosmology. The universe's age would need recalculation. The history of structure formation, how galaxies clustered over time, would need revision. Predictions about the universe's ultimate fate would shift. Instead of a steadily accelerating heat death, we might face a big rip, where dark energy grows so strong it eventually tears apart galaxies, stars, planets, atoms themselves. Or dark energy could weaken and reverse, leading to a big crunch, where expansion halts and the universe collapses. The entire cosmic narrative hangs on whether W equals -1 or not. You shift under your blanket, feeling the weight of invisible energy permeating every cubic centimetre of space, gently pushing reality apart. Dark energy is the universe's most abundant ingredient, yet we don't know what it is, how it works, or whether it's constant. JWST is providing the most precise measurements yet of its behaviour over cosmic history, and those measurements are suggesting that the simple, elegant cosmological constant might be too simple. The universe's accelerating expansion might be driven by something stranger, something dynamic, something we haven't properly identified yet despite it making up more than 2/3 of everything. Einstein's model might survive, or it might need a new chapter, one we haven't written yet, waiting to be decoded from JWST's observations of ancient light. You're floating in the comfortable darkness, and it's time to confront cosmology's most humbling fact. We've only accounted for about 5% of the universe. Everything you've ever seen, touched, or measured directly, every star, planet, nebula, and particle, makes up a tiny fraction of what exists. The remaining 95% is split between dark matter, roughly 27%, and dark energy, roughly 68%. Two mysterious components that reveal themselves only through their gravitational effects and their influence on cosmic expansion. We can't see them, can't touch them, can't capture them in laboratories, yet they dominate the universe's composition and fate. And JWST's discoveries are suggesting that this dark sector, the 95% we don't understand, is even stranger and more complex than the already bizarre models predicted. Dark matter was first seriously proposed in the 1930s by astronomer Fritz Zwicky, who noticed that galaxies in the Coma cluster were moving far too fast to be held together by the gravity of their visible matter alone. The cluster should have flown apart eons ago unless there was additional invisible mass providing extra gravitational glue. His calculation suggested the cluster contained 400 times more dark matter than luminous matter, a result so extreme that most astronomers dismissed it as a measurement error. Zwicky called his colleagues spherical bastards, because they were bastards no matter which way you looked at them, and history eventually proved him right. though it took 4 decades for the evidence to become undeniable. The modern case for dark matter rests on multiple independent pillars: galaxy rotation curves, the way stars orbit around galactic centers, require dark matter halos extending far beyond visible disks. Gravitational lensing, where massive objects bend light from background sources, reveals invisible mass distributions matching dark matter predictions. The cosmic microwave background's temperature fluctuations encode information about the universe's matter content, pointing unmistakably toward abundant dark matter, and computer simulations of cosmic structure formation can't reproduce the universe's observed web-like pattern of galaxy clusters without dark matter's gravitational scaffolding. The evidence is overwhelming, even if we still don't know what dark matter particles actually are. Leading candidates include WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and the weak nuclear force, making them almost impossible to detect directly. Decades of underground experiments have searched for WIMPs colliding with atomic nuclei, so far without success, which is pushing theorists toward alternative candidates like axions, ultralight particles originally proposed to solve a problem in quantum chromodynamics, or sterile neutrinos, hypothetical cousins of known neutrinos. The dark matter mystery remains unsolved, one of physics' most embarrassing gaps. Now here's where JWST complicates the picture. Observations of galaxy distributions at high redshifts, combined with measurements of the early universe's structure, are revealing tensions in how dark matter behaves. Some data suggest dark matter might have self-interactions, that dark matter particles occasionally collide with each other, rather than passing through one another like ghosts. This would affect how dark matter clumps in galaxy cores, potentially solving long-standing problems like why simulations predict cuspy-dense centers, while observations show flatter distributions. But self-interacting dark matter requires new physics beyond the standard WIMP model, adding complexity to an already mysterious phenomenon. There's also the satellite galaxy problem. Simulations predict that large galaxies like the Milky Way should be surrounded by thousands of small dark matter halos, each potentially hosting a dwarf galaxy. We only observed dozens. Where are the missing satellites? Maybe they're there but failed to form stars, remaining invisible dark matter clumps. Or maybe dark matter physics is more complicated than our simplest models assume, with temperature-dependent interactions or connections to dark energy that suppress small-scale structure formation. JWST's observations of the early universe's galaxy populations are providing new constraints on these scenarios, and so far the simplest models aren't fitting perfectly. A quirky detail that highlights our ignorance. We don't even know if dark matter is one thing or many. The dark sector could be as complex as the visible sector, with multiple types of dark particles, dark forces, even dark chemistry forming dark atoms and molecules. Some theoretical frameworks propose dark photons, mediating forces between dark matter particles, or asymmetric dark matter models where dark matter has antimatter counterparts that mostly annihilated in the early universe, leaving a residue similar to the matter-antimatter asymmetry that produced ordinary matter. These ideas sound like science fiction, but they're taken seriously because our current understanding is so incomplete. Dark energy, as we discussed earlier, is even more mysterious because we can't even narrow down whether it's a field, a particle, a property of space, or a sign that general relativity fails at cosmic scales. The lambda CDM model simply parameterizes it as a constant, acknowledging that we don't understand its nature. Together, dark matter and dark energy constitute 95% of the universe's mass-energy budget, and we're essentially ignorant about both. Scholars still argue about whether the dark sector components are truly separate entities, or different manifestations of a single underlying phenomenon. Some unified dark matter, dark energy models propose a single field that behaves like dark matter when dense, in galaxies, and like dark energy when diffuse, in cosmic voids. Others suggest modifications to gravity itself, theories like MOND, modified Newtonian dynamics, or MOG, modified gravity, that eliminate the need for dark matter by changing how gravity behaves at low accelerations or large scales. Mainstream cosmology remains skeptical because these theories struggle to explain all observations simultaneously, but the sheer mystery of the dark sector keeps alternatives alive. JWST's contribution to this puzzle is mapping how structure formed in the early universe, tracking how dark matter's gravitational influence shaped the distribution of galaxies over billions of years. The more precise these observations become, the tighter the constraints on dark matter's properties. Some JWST data is already suggesting that dark matter might be warmer than previously thought, moving at higher velocities in the early universe, which would smooth out structure on small scales. This pushes away from the coldest, most sluggish dark matter candidates and toward particles with small but non-negligible velocities. You nestle deeper into your pillow, contemplating a universe where everything you can see and measure is just the foam on an invisible ocean. The stars and galaxies are tracers, markers floating on currents of dark matter, pushed apart by dark energy's inexorable pressure. We're like sailors mapping coastlines while remaining utterly ignorant of the deep ocean's ecology, chemistry, and inhabitants. JWST is giving us better maps of the coastlines, revealing patterns that hint at what lies beneath, but the vast dark depths remain fundamentally mysterious. The 5% we understand is impressive: nuclear physics, electromagnetism, chemistry, biology, consciousness itself. But it's a tiny island in a dark sea, and JWST's observations keep reminding us that the sea is deeper and stranger than our brightest theories predicted. We live in a universe we barely comprehend, dominated by components we can't identify, and somehow we're arrogant enough to call ourselves cosmologists. You're drifting now through the space between galaxies, the vast cosmic voids where light years stretch empty and cold. And here's where JWST has uncovered something both eerie and profound: rogue planets. Billions upon billions of them, maybe trillions, wandering the darkness without stars to orbit, without suns to warm them, cosmic orphans ejected from their birth systems or formed in isolation, invisible until JWST's infrared eyes caught their faint heat signatures glowing against the absolute zero of intergalactic space. These aren't rare oddities. They might actually outnumber stars, a hidden population of worlds drifting through the void, and the implications for planetary formation, for the sheer abundance of planet-sized objects in the universe, are staggering enough to rewrite every estimate we've made about how common worlds actually are. The concept of rogue planets isn't new. Astronomers have theorized about their existence for decades. During planetary system formation, when young planets jostle for stable orbits around newborn stars, gravitational interactions can fling smaller worlds into interstellar space like cosmic billiard balls knocked off the table. Computer simulations of solar system formation consistently show that for every planet that achieves a stable orbit, one or more gets ejected. In our own solar system's early history, there were probably additional planets, perhaps an ice giant between Saturn and Uranus, or super-Earths in the inner system, that got gravitationally booted into the Milky Way's depths during the chaotic shuffling phase. They're out there somewhere, frozen and dark, carrying the solar system's chemical signature into eternal exile. But theoretical predictions and actual detections are different things. Rogue planets are extraordinarily difficult to observe because they emit virtually no light, no star to reflect, no internal fusion to generate energy, just the faint infrared glow of residual heat from their formation, slowly radiating into space over billions of years. Ground-based telescopes occasionally catch them through gravitational microlensing. When a rogue planet passes in front of a distant star and its gravity briefly magnifies the star's light. But these detections are fleeting and rare. JWST, with its exquisite infrared sensitivity and ability to stare at patches of sky for extended periods is changing the game entirely. Early JWST surveys of star-forming regions and galactic peripheries have detected far more free-floating planetary mass objects than expected. Worlds with masses ranging from Jupiter-sized down to potentially Earth-sized, floating in the darkness with no parent star. Some of these are young, still warm from formation, glowing brightly enough in infrared that JWST can image them directly. In the Orion Nebula cluster, for instance, JWST identified dozens of Jupiter mass objects that appear to have formed in isolation, condensing directly from gas clouds rather than being ejected from planetary systems. If this direct collapse formation mechanism is common, it means the universe is manufacturing planets not just around stars but scattered throughout molecular clouds, factory production on a cosmic scale. Here's the mind-bending extrapolation. If star-forming regions produce one rogue planet for every star, and if dynamical ejection adds another 1 or 2 rogues per planetary system, then the Milky Way alone could contain 50 billion to 200 billion rogue planets, far outnumbering the galaxy's 100 billion to 400 billion stars. Scale that to the observable universe's estimated 2 trillion galaxies, and you're looking at something like 100 quintillion to 400 quintillion rogue planets. A number so large it loses meaning, a population of worlds exceeding stars by orders of magnitude. The universe isn't primarily made of stars, it's made of dark, frozen worlds tumbling through emptiness. The mainstream scientific reaction has been a mixture of excitement and urgency to revise planetary census models. Every estimate of Earth-like planets, or potentially habitable worlds, has focused on planets orbiting stars within habitable zones, where liquid water could exist on surfaces. Nobody seriously counted rogues because they're frozen ice balls, lifeless by any conventional definition. But the sheer number changes statistical arguments about planetary formation efficiency, about the total mass locked up in planetary bodies versus stars, about the distribution of heavy elements throughout galaxies. If rogue planets are as common as JWST suggests, they represent a significant fraction of the universe's ordinary matter, a component that previous surveys simply missed because it was invisible. There's a quirky detail worth mentioning. Some rogue planets might not be completely frozen. Models suggest that massive rogue planets, super Jupiters with tens of Earth masses, could retain internal heat from radioactive decay and gravitational contraction for billions of years, potentially maintaining subsurface oceans beneath thick ice shells, similar to Jupiter's moon Europa or Saturn's moon Enceladus. These oceans would be completely isolated from starlight, heated only by internal processes, but thermochemical reactions could theoretically support microbial life. It's wildly speculative, but the statistical argument is compelling. If even 1 in a million rogue planets harbours subsurface life, and there are quintillions of rogues, then life in the universe might be far more abundant than we've imagined, just hidden in darkness, beyond the reach of conventional biosignature. Searches focused on planets orbiting stars. Scholars still argue about formation mechanisms. The direct collapse scenario, where turbulent gas clouds fragment into planet mass clumps without forming stars, challenges conventional wisdom that planets require protoplanetary disks around stars. Some researchers propose that these objects should be called sub-brown dwarfs, or planetary mass objects, rather than planets, reserving planet for objects that formed in circumstellar disks. It's semantic hair-splitting, but terminology matters when you're trying to define categories. If an object has planetary mass but formed like a star through gravitational collapse, is it truly a planet, or is it a failed star? The International Astronomical Union will probably spend years debating definitions, as they did with Pluto's demotion. There's also the fringe idea, entertained more in science fiction than peer-reviewed journals, that advanced civilizations might preferentially inhabit rogue planets. The logic goes, rogue planets are invisible, mobile, and effectively unlimited in number. A civilization wanting to remain hidden from predatory neighbours could engineer their world's ejection from its star system, power their society with fusion reactors or core heat, and drift through intergalactic space in perfect concealment. JWST's discovery that rogues vastly outnumber stars makes this scenario slightly less absurd. There's certainly no shortage of real estate. Of course, there's zero evidence for this, but it's the kind of speculation that emerges when you discover the universe contains quintillions of hidden worlds. You pull your blanket tighter, imagining frozen super-Earths tumbling through the dark between galaxies, their surfaces locked in eternal ice, their skies devoid of stars, their trajectories carrying them nowhere in particular across billions of years. Some were ejected violently during planetary system chaos, flung outward at escape velocity, carrying the chemical fingerprints of their birth systems into exile. Others condensed alone in the depths of molecular clouds, never knowing the warmth of a parent star, born orphans in the cosmic cold. And JWST, peering into the infrared darkness, is finally revealing them, proving that the universe's population of worlds is far, far larger than we ever counted. The space between galaxies isn't empty. It's filled with silent worlds, adrift in the endless night, outnumbering the stars themselves. You're hovering now above the universe at its largest scale, pulling back until galaxies shrink to pinpoints and the cosmic structure reveals itself in all its strange, beautiful geometry, and what you see isn't a random scatter of galaxies but an intricate web. Vast filaments of matter connecting dense nodes where galaxy clusters gather, separated by enormous voids where almost nothing exists. A foam-like structure that astronomers call the cosmic web. We've known about this pattern for decades through painstaking surveys that mapped galaxy positions across billions of light years. But JWST is doing something unprecedented. It's revealing the web's actual physical structure, the diffuse hydrogen gas threading between galaxies along those filaments, the scaffolding itself rather than just the buildings constructed upon it, and the images are breathtaking in their clarity and unsettling in what they imply about how structure formed in the early universe. The cosmic web emerges from the universe's initial conditions, those quantum fluctuations in the first fraction of a second after the Big Bang that got stretched to cosmic scales during inflation. These tiny density variations, some regions slightly denser, others slightly less so, became the seeds for all future structure. Denser regions had stronger gravity, attracting surrounding matter, growing over time while underdense regions became voids as material drained away toward denser neighbours. Dark matter, immune to radiation pressure and electromagnetic forces, collapsed first into halos that formed the gravitational framework. Normal matter, hydrogen and helium gas, fell into these dark matter scaffolds, creating the filaments we observe today. It's a bottom-up process, driven by gravity's patient accumulation over billions of years. Mainstream cosmology has mapped the cosmic web's galaxy distribution with increasing precision since the 1980s. The CFA Redshift survey first revealed the Great Wall, a massive sheet of galaxies stretching across hundreds of millions of light-years. Subsequent surveys, the 2-degree field, the Sloan Digital Sky Survey, the BOSS survey, mapped tens of millions of galaxies, revealing that the web structure extends across the entire observable universe with remarkable consistency. Filaments are typically 150 to 300 million light-years long and 20 to 30 million light-years wide, containing most of the universe's galaxies. Voids occupy about 60% of space, but contain less than 10% of the universe's matter. It's an extremely uneven distribution, matter clustered along filaments, while vast regions remain nearly empty. But here's what previous surveys couldn't see: the gas itself, the diffuse intergalactic medium that makes up most of the universe's ordinary matter. The hydrogen between galaxies is too spread out and too cold to emit much light, rendering it essentially invisible to conventional telescopes. We inferred its existence from absorption lines. When light from distant quasars passes through intervening gas clouds, specific wavelengths get absorbed, leaving dark gaps in the spectrum. This technique, called the Lyman alpha forest because it creates a thicket of absorption lines, proved that intergalactic hydrogen exists, but it couldn't map its distribution in 3 dimensions. JWST, with its infrared sensitivity and spectroscopic capabilities, is changing that, detecting faint emission from hydrogen and heavier elements along filaments, creating the first direct images of the cosmic web's connective tissue. The resolution and clarity are stunning. JWST images of galaxy clusters now show faint tendrils of glowing gas stretching between member galaxies, tracing the filaments predicted by simulations. In some cases, the gas is fluorescing under ultraviolet radiation from nearby galaxies or quasars, making it temporarily bright enough to image directly. In others, JWST detects the gas's subtle absorption against background light sources, mapping its 3-dimensional distribution. It's like finally seeing the mycelium network connecting mushrooms in a forest. The structure was always there, but now we can photograph it, measure it, analyze its chemistry and temperature and density. Here's a quirky detail that illustrates the web's scale and strangeness. The filaments contain roughly half of the universe's ordinary matter, but they're so diffuse that the density averages about 1 atom per cubic meter, far emptier than the best vacuum humans can create in laboratories. Yet because the filaments are so enormous, spanning hundreds of millions of light years, their total mass is staggering. The gas is also surprisingly hot, heated to 100,000 to 10 million Kelvin by shocks and gravitational compression as it falls into filaments. This is the warm-hot intergalactic medium, or UHIM, which solves the missing baryon problem. For years, astronomers couldn't account for about 40% of the universe's ordinary matter. Turns out it was hiding in filaments, too hot to emit much visible light, but detectable in ultraviolet and X-ray wavelengths, and now increasingly visible to JWST's instruments. Scholars still argue about how exactly the cosmic web formed in its current configuration. The basic gravitational story is solid. Overdensities attract matter, forming filaments and nodes, but the details are contentious. How quickly did the web emerge? Did dark matter halos form first and then attract gas, or did gas and dark matter co-evolve? What role did early galaxy feedback, radiation and winds from the first stars and quasars, play in shaping the web's structure? Simulations can reproduce the web's large-scale pattern, but matching all the observational details, filament widths, void sizes, gas temperatures, chemical enrichment levels, requires tweaking numerous parameters, and there's ongoing debate about which physical processes are most important. JWST's observations are now constraining these models with unprecedented precision. By mapping the web structure at different cosmic epochs, looking at nearby regions where we see the web today, then progressively more distant regions showing the web billions of years ago, researchers can track how the structure evolved. Early results suggest the web formed earlier and more coherently than some models predicted, with well-defined filaments already visible when the universe was just 2 billion years old. That's impressively fast, implying that matter clumped efficiently even in the chaotic early cosmos, and it adds to the growing pile of evidence that structure formation in general was more vigorous than standard models anticipated. There's also a fringe theory worth mentioning. Some researchers have proposed that the cosmic web's specific geometry, the particular arrangement of filaments and voids, encodes information about the universe's global topology, its overall shape and connectivity. Most cosmologists assume the universe is simply connected and infinite, extending forever in all directions, but alternatives exist. The universe could be finite and wrap around on itself like the surface of a hypersphere, or it could have a more complex multiply connected topology like a 3-dimensional torus. If true, The cosmic web's pattern at the larger scales would show subtle repetitions or correlations that reveal this topology. JWST's deep surveys might eventually cover enough volume to test these ideas, though most physicists are skeptical that we'll find evidence for exotic topologies. You sink deeper into your cocoon, imagining the universe as a vast neural network, filaments like axons connecting nodes of galaxies, signals of light and matter flowing along connections forged by gravity over billions of years. The cosmic web is the universe's anatomy, its skeleton and circulatory system combined, the infrastructure on which everything else is built. JWST has given us the first clear images of this infrastructure's finest details, revealing that the space between galaxies isn't empty, but threaded with warm gas, stitched together by dark matter's invisible gravity, organised into a structure of almost biological complexity. The universe has bones, and we're finally seeing them in their full skeletal beauty. You're settling into that delicious heaviness where thoughts become dreamlike, and now we need to discuss something that sounds like science fiction, but is increasingly supported by JWST's data. Primordial black holes, microscopic to asteroid-sized black holes that formed in the universe's first second, not from collapsing stars but from density fluctuations in the immediate aftermath of the Big Bang, and they might be everywhere. Not just scattered here and there as cosmic curiosities, but genuinely abundant, perhaps numerous enough to account for all or most of dark matter, drifting invisibly through space, occasionally passing through your body at this very moment, their gravity so localized and their passage so brief that you'd never notice. It's one of the most elegant solutions to the dark matter mystery, and JWST is providing indirect evidence that these ancient black holes might outnumber stars. The idea of primordial black holes dates back to the early 1970s, when physicists Stephen Hawking and Bernard Carr explored what might happen during the universe's first moments when matter was compressed to extraordinary densities. In those initial microseconds, quantum fluctuations could create regions dense enough to collapse directly into black holes without needing a star's death as an intermediary. These wouldn't be the stellar mass black holes formed from supernovae, nor the supermassive monsters at galaxy centres. Primordial black holes could span an enormous mass range, from microscopic black holes lighter than a paperclip to behemoths thousands of times more massive than the Sun, all depending on exactly when and how they formed in that chaotic primordial soup. For decades, primordial black holes remained a theoretical curiosity, interesting but lacking observational support. The mainstream focus for dark matter stayed on particle candidates like WIMPs, but as direct detection experiments kept coming up empty, decades of underground detectors failing to catch a single WIMP interaction, some researchers began revisiting primordial black holes as a serious alternative. After all, black holes are made of ordinary matter, or at least they were, before collapsing beyond the event horizon, so they don't require inventing new particles. They interact only through gravity, exactly like dark matter should, and they're naturally invisible, detectable only through gravitational effects. The match is almost too perfect. Here's where JWST enters the story. The telescope's observations of gravitational lensing events, instances where a massive foreground object bends and magnifies light from background sources, are revealing more lensing than expected from known galaxies and galaxy clusters alone. Some of this excess lensing could be explained by primordial black holes scattered along the line of sight, their gravity focusing light even though they're individually undetectable. Additionally, JWST's detection of those impossibly early, supermassive black holes we haven't fully discussed yet, that's coming later, patience, could be explained if seeds for those black holes were primordial black holes that formed in the first second, giving them a massive head start on growth. Statistical analyses of JWST's deep field images show subtle correlations in how background galaxies are distorted by foreground mass, and when researchers model what's causing these distortions, they find that including a population of intermediate mass primordial black holes, roughly 10 to 100 solar masses each, improves the fit significantly. It's not definitive proof, but it's compelling circumstantial evidence. If primordial black holes in this mass range are abundant enough to constitute even 10 to 20% of dark matter, they'd produce exactly the kind of lensing signatures JWST is detecting. There's a quirky historical twist here. For years, one of the main arguments against primordial black holes as dark matter was that they should produce frequent microlensing events, temporary brightenings of distant stars as a black hole passes in front of them, magnifying their light. Surveys of millions of stars in the Magellanic Clouds and toward the galactic center found far fewer microlensing events than expected if most dark matter were in black holes. This seemed to rule out primordial black holes in certain mass ranges, but those surveys were sensitive primarily to black holes in a narrow mass window, roughly 0.1 to 10 solar masses. Primordial black holes outside this range, either much smaller, asteroid mass, or much larger, 100 plus solar masses, would evade those constraints. JWST's observations are sensitive to lensing by larger black holes and to the collective effects of many small ones, probing parameter space that previous surveys missed. Scholars still argue intensely about whether primordial black holes can be the dominant dark matter component. Some researchers point out that they'd affect the cosmic microwave background's temperature fluctuations in ways not observed, though these constraints depend on assumptions about exactly when the black holes formed and how they're distributed. Others note that if primordial black holes were abundant, we should see more binary black hole mergers, events where two black holes spiral together and merge, releasing gravitational waves. The LIGO and Virgo observatories have detected dozens of such mergers, and some of the detected black hole masses are suspiciously in the range where primordial black holes might exist, neither light enough to be typical stellar remnants, nor heavy enough to be supermassive. Could some of LIGO's detections be primordial black holes colliding? It's possible, though proving it requires distinguishing primordial origins from stellar origins, which is devilishly difficult. The mathematics of primordial black hole formation is fascinating and strange. They would have formed during specific windows in the universe's first second, when density fluctuations crossed a critical threshold. Too small, and gravity couldn't overcome pressure to collapse them. Too large, and they'd have formed even earlier or differently. The mass distribution of primordial black holes depends sensitively on the spectrum of density fluctuations imprinted during inflation, which means detecting a population of primordial black holes would actually teach us about physics at energy scales far beyond what particle accelerators can reach. It's cosmology doing the work of particle physics, probing the universe's earliest moments through their fossilized remnants. There's also the truly fringe speculation that some primordial black holes might be naked singularities without event horizons, which would violate the cosmic censorship hypothesis, but might be allowed under exotic formation conditions in the early universe, or that they could have formed from phase transitions as the universe cooled, like ice crystals forming in supercooled water, rather than from density fluctuations. These ideas are extremely speculative, living on the boundary between physics and mathematical curiosity, but the point is that primordial black holes, if confirmed, would open entirely new windows into fundamental physics. You shift slightly, your breathing slow and deep, and you imagine microscopic black holes passing through the Earth, through your bedroom, through your body. Billions of them perhaps, each a tiny knot of warped space-time, descendants of the universe's first second, older than any star or galaxy, survivors of nearly 14 billion years of cosmic evolution. They don't interact with matter, except through gravity's gentle tug, so they pass through solid objects like ghosts, their event horizons smaller than atomic nuclei for the smallest ones, undetectable individually, but collectively shaping the universe's structure through their gravitational influence. JWST is slowly building the case that these ancient relics might be far more common than anyone suspected. that dark matter's mystery might have a solution that's simultaneously simpler and stranger than exotic particles. The universe could be filled with black holes that predate everything else, invisible architects of cosmic structure, and we're only now gathering the evidence to prove they're there. Primordial ghosts from the universe's birth, outnumbering the stars, drifting through eternity, and possibly through you, right now, as you drift towards sleep. You're floating in that twilight space where physics becomes philosophy, and here's where JWST's observations start brushing against one of the most controversial ideas in cosmology, the multiverse, the notion that our universe isn't alone but is instead one bubble among infinite others, each with potentially different physical laws, different constants of nature, different outcomes for how reality unfolds. For decades, the multiverse remained firmly in the realm of theoretical speculation, unfalsifiable and therefore unscientific according to strict definitions. But JWST's deep field images are revealing quantum fluctuations frozen into the large-scale structure of the cosmos, patterns that align eerily well with predictions from eternal inflation theory, the framework that naturally produces a multiverse. And while it's not proof, it's the closest thing to observational support that multiverse advocates have ever had. The multiverse concept emerges from inflation theory, which was developed in the early 1980s by Alan Guth and others to solve several problems with the standard Big Bang model. The original Big Bang theory couldn't explain why the universe is so uniform in temperature and density across vast distances that were never in causal contact. There wasn't enough time for different regions to exchange information and equilibrate. It also couldn't explain why space is so geometrically flat, balanced precisely between open and closed curvatures. Inflation solved both problems elegantly. A brief period of exponential expansion in the universe's first fraction of a second, driven by a hypothetical inflaton field, stretched the universe so rapidly that any initial irregularities or curvature got smoothed out, like inflating a wrinkled balloon, until its surface appears perfectly smooth. But here's the cosmological catch. If inflation happened once, it probably happened many times, and might still be happening in distant regions of space beyond our observable horizon. The inflaton field doesn't necessarily decay everywhere simultaneously. Instead, quantum fluctuations cause it to decay at different rates in different locations, creating a patchwork of bubble universes, nucleating within a still inflating background. Each bubble becomes a universe with its own Big Bang-like expansion history, its own physical properties determined by how the field settled into their vacuum states. This is eternal inflation, and it naturally produces a multiverse, not by design or metaphysical speculation, but as an inevitable mathematical consequence of the inflation mechanism combined with quantum mechanics. Mainstream cosmology has a complicated relationship with the multiverse. On one hand, inflation theory is widely accepted because it elegantly explains observations, the cosmic microwave background's uniformity, the flatness of space, the spectrum of density fluctuations that seeded galaxy formation. On the other hand, eternal inflation and its multiverse implications make many physicists uncomfortable, because other universes are, by definition, beyond our observational reach. If you can't detect something even in principle, can you claim it exists scientifically? The debate gets philosophical quickly, with some arguing that a theory's consequences must be accepted even if unobservable, while others insist that science must remain strictly empirical. Enter JWST with its exquisitely detailed observations of the cosmic microwave background's imprint on large-scale structure, and here's where things get interesting. Inflation predicts that quantum fluctuations during the inflationary epoch got stretched to cosmic scales, imprinting a specific statistical pattern on the distribution of matter, nearly scale invariant with tiny deviations, Gaussian to high precision, but with subtle non-Gaussian features. These predictions match observations remarkably well, but eternal inflation adds an extra wrinkle. If our universe nucleated from a larger inflating background, there should be extremely subtle anomalies at the larger scales, slight deviations from perfect randomness that reflect the geometry and dynamics of how our bubble formed. JWST's observations of large-scale structure at high redshift, combined with cosmic microwave background data from Planck, are revealing potential anomalies, slight asymmetries between opposite hemispheres of the sky, unexpected correlations at the largest angular scales, and a peculiar lack of power in the lowest multipoles. Essentially, the universe looks slightly more uniform at the bigger scales than inflation's simplest models predict. These anomalies are statistically marginal, dancing right at the edge of significance, but they align with some eternal inflation scenarios where our observable universe occupies a small patch near the wall of our bubble universe, and interactions or proximity effects from the larger multiverse structure introduce subtle distortions. Here's a quirky detail that makes this feel almost surreal. Some multiverse models predict that physical constants, things like the electron's charge, the strength of gravity, the mass of the Higgs boson, vary between bubble universes, determined randomly by how fields settle during each bubble's formation. Our universe's constants appear finely tuned for life, strengthen gravity slightly or weaken electromagnetism a bit, and stars wouldn't form properly, or atoms wouldn't bond into molecules, or any of a dozen other catastrophes would prevent complexity from emerging. The anthropic explanation says there's no mystery. In a multiverse with countless variations, we necessarily find ourselves in a rare universe where the constants permit our existence, because we couldn't exist in the vast majority of bubbles where conditions are inhospitable. It's selection bias on a cosmic scale. We observe the universe we do because it's the kind of universe that produces observers. Scholars still argue vehemently about whether anthropic reasoning is legitimate science or circular philosophy. Critics say it's unfalsifiable and therefore meaningless. You can explain any observation by saying, if it were different, we wouldn't be here to ask the question. Proponents counter that anthropic reasoning makes testable predictions. If fine-tuning is anthropic rather than fundamental, we should expect to find ourselves in a universe that's just barely suitable for life, not excessively so. And indeed, some constants do seem barely adequate. Increase the cosmological constant, dark energy strength, by a factor of 2, and galaxies wouldn't form. Our universe is right at the edge of viability, consistent with anthropic selection. JWST's contribution is mapping the universe's large-scale structure with unprecedented precision, allowing tests of inflation's predictions at the finest level yet. Some theorists argue that if we find definitive evidence of certain patterns, like circular temperature variations in the cosmic microwave background, that could represent collisions between bubble universes during their early expansion, it would constitute indirect detection of the multiverse. Others remain skeptical, noting that multiple theoretical frameworks can produce similar patterns, and distinguishing them requires assumptions about physics beyond what we can test directly. There's also the simulation hypothesis angle, which occasionally gets entangled with multiverse discussions. If universes are abundant and varied, and if advanced civilizations develop the capability to simulate universes, running cosmic evolution as a computation, then simulated universes might vastly outnumber real ones, making it statistically likely we're in a simulation. Some JWST images show what appear to be pixelation-like effects at extreme magnifications, discrete patterns suggesting a fundamental graininess to space-time, but these are more plausibly explained by quantum mechanics or quantum gravity effects, rather than evidence we're living in a cosmic computer program. Still, it's the kind of speculation that emerges when you start seriously considering that reality might be far larger and stranger than what we directly observe. You pull the blanket up to your ears, your mind swirling with images of infinite bubbles, each a universe unto itself, some containing galaxies and stars, others dark and formless, some with laws of physics that permit complexity, most sterile and lifeless. Our universe, this vast expanse of billions of galaxies spanning billions of light years, might be just one small bubble in an infinite foam, and JWST's observations, those quantum fluctuations frozen into cosmic structure, those subtle anomalies at the largest scales, might be the faintest whispers from beyond our bubble's walls, hints that reality extends far beyond everything we can ever hope to see. The multiverse gets mathematical, the math gets observational, and somehow, lying in your bed in the quiet dark, you're connected to the grandest question of all. Is there only one universe, or are there countless others, forever beyond reach but mathematically inevitable, each playing out its own cosmic story in the infinite space beyond our horizon? JWST doesn't answer the question definitively, it can't. But it's gathering the data that brings the question from philosophy into the realm of testable science. One deep field image at a time. You're sinking deeper now, consciousness fading at the edges like an old photograph, and it's time to circle back to one of the most perplexing discoveries JWST has made. The timeline of star formation, specifically the appearance of first-generation stars, population 3 stars, pristine giants made purely of hydrogen and helium from the Big Bang, no heavier elements contaminating their composition, showing up in the cosmic record a full 100 million years earlier than any model allowed. These stars were supposed to be the universe's pioneers, igniting around 100 to 200 million years post-Big Bang, but JWST is detecting their signatures at redshifts corresponding to 50 to 80 million years after the beginning. And that compression of the timeline doesn't just tweak stellar evolution theory, it fundamentally challenges our understanding of how gravity, gas dynamics, and chemistry conspire to light the universe's first fires. Population 3 stars have never been directly observed in the modern universe, because they all died billions of years ago, their brief violent lives ending in supernovae that scattered their ashes, the first carbon, oxygen, iron, and other heavy elements, into space, seeding the next generation of star formation. The closest we've come to seeing them is detecting their indirect effects, the chemical signatures they left behind in extremely metal-poor stars born from their debris, and the theoretical predictions about how they should have looked. Models suggest population 3 stars were monsters, typically 100 to 300 solar masses, thousands of times brighter than the sun, burning through their fuel in just a few million years before exploding. They had to be massive because primordial gas clouds lacked heavy elements that facilitate cooling. Without carbon and oxygen to radiate energy away, gas clouds couldn't fragment into smaller clumps, so stars formed at much higher masses than the sun-sized stars common today. The mainstream timeline, calibrated through decades of simulations and observations of the cosmic microwave background, placed the first population 3 stars around 100 million years after the Big Bang. This gave time for dark matter halos to grow large enough to trap significant amounts of gas, for that gas to cool and compress despite lacking efficient coolants, and for molecular hydrogen, the only coolant available in primordial gas, to form in sufficient quantities. The process was gradual, patient, governed by the inexorable mathematics of gravitational collapse and thermodynamics. First stars ignite, they irradiate their surroundings with ultraviolet light. They begin ionizing the neutral hydrogen filling space. They explode and enrich nearby regions with metals, and gradually the universe transitions from dark to luminous over several 100 million years. JWST is detecting spectroscopic signatures of population 3 star activity, specifically unusual emission line ratios indicating extremely low metallicity and the presence of highly energetic photons capable only of being produced by very massive, very hot stars in galaxies at redshift around Z equals 15 to Z equals 20, corresponding to 50 to 80 million years after the Big Bang. That's absurdly early. At those epochs, Dark matter halos should barely have begun forming, gas densities should be low, temperatures should be too high for efficient collapse. Yet somehow stars ignited anyway, and not just a few rare pioneers, but enough to light up detectable galaxies that JWST can image across billions of light years. Here's where the physics gets uncomfortable. Star formation requires cooling, and cooling in primordial gas is limited by molecular hydrogen's radiative efficiency, which depends on temperature and density in well-understood ways. You can't arbitrarily speed up the process without violating thermodynamics. So if stars formed 100 million years earlier than models predict, either the initial conditions were different, perhaps the primordial gas was denser or had different temperature profiles than assumed, or there's a cooling mechanism we haven't accounted for, or dark matter clumped more efficiently and created deeper gravitational potential wells earlier, or some combination of factors we haven't properly modelled. One quirky possibility researchers are exploring: magnetic fields. The early universe is often modelled as having weak or negligible magnetic fields, but if primordial fields were actually significant, perhaps generated during the phase transitions immediately after the Big Bang, they could have affected how gas collapsed and cooled, channeling material along field lines and creating denser clumps that fragment into stars more readily. This is speculative, requiring magnetic field strengths and configurations we can't directly observe, but it's the kind of adjustment that could accelerate star formation without breaking fundamental physics. The devil, as always, is in quantitative details. Can reasonable magnetic fields shift the timeline by 100 million years? The jury is still out. Scholars still argue about whether JWST's detections are genuinely population 3 signatures or contaminated by later generation stars. Spectroscopy at these distances is challenging. Light is faint, red-shifted into wavelengths where Earth's atmosphere or instrumental noise create complications, and interpreting emission line ratios requires assumptions about the ionizing radiation field and gas geometry that might not be accurate. Some researchers caution that what looks like pristine population 3 activity might actually be metal-poor population 2 stars, second-generation stars with trace heavy element content, masquerading as population 3, or that unusual ionization conditions in early galaxies could mimic population 3 spectral signatures without actual zero metallicity stars being present. But the weight of evidence is accumulating. Multiple independent observations of different high redshift galaxies show consistent patterns: extremely hard ionizing radiation, unusual helium emission, lack of metals, all pointing toward massive primordial stars. If it's a systematic error or misinterpretation, it's a remarkably consistent one affecting multiple instruments and analysis methods. The conservative interpretation is that population 3 stars formed somewhat earlier and more abundantly than the simplest models predicted, requiring modest revisions to theory. The radical interpretation is that our entire framework for early star formation needs rebuilding from the foundation, that we're missing major physical processes or initial conditions. There's also the timing cascade effect. If first stars formed 100 million years early, they enriched their surroundings with metals earlier, which means population 2 stars, the second generation, also formed earlier, which means small galaxies assembled earlier, which means everything downstream in cosmic history happens on a compressed timeline. This cascades through the entire narrative of structure formation, potentially explaining why JWST finds massive galaxies at absurdly early times. If star formation got a head start, galaxies had more time to grow, and what looked impossible under the old timeline becomes merely improbable under the revised one. It's not a complete solution, but it helps reduce the tension between observations and theory. Then there's the fringe idea that some of the ultra-early luminous objects JWST detects aren't stars at all, but dark stars. Hypothetical stars powered not by nuclear fusion, but by dark matter annihilation. If dark matter particles collide and annihilate in the dense cores of primordial gas clouds, the energy released could heat the gas and create pressure support, forming star-like objects that glow brightly without needing to achieve the temperatures and densities required for fusion. Dark stars could form earlier than fusion-powered stars because they don't require the same cooling and compression thresholds. It's a wild idea, proposed seriously by a handful of researchers, testable in principle by looking for spectroscopic signatures that differ from normal stars, but so far lacking definitive evidence. JWST might eventually confirm or rule out dark stars by analysing the spectra of ultra-distant luminous sources in detail. You nestle deeper, you're breathing slow and rhythmic, and you imagine the universe's first stars igniting against the darkness, their ultraviolet light carving spheres of ionized gas in the neutral hydrogen fog, their radiation beginning the long process of reionization that would eventually make the universe transparent to light. These pioneers formed earlier than we thought, burned brighter than we expected, and left their chemical fingerprints scattered across billions of light years for JWST to detect. The universe was precocious in every respect. Galaxies too soon, stars too early, structure assembling at breakneck speed compared to our leisurely models, and we're still catching up, revising timelines, adjusting theories, trying to understand how the cosmos managed to do so much so fast in its frantic youth. The first light in the universe came earlier than we predicted, and the implications ripple through every epoch that followed. You're drifting through a cosmic current, your bedroom dissolved into the fabric of space-time itself. And now, we need to discuss something both mysterious and gravitationally inevitable. The Great Attractor, a massive concentration of mass some 220 million light-years away in the direction of the constellations Triangulum Australe and Norma, pulling our Milky Way galaxy and tens of thousands of neighbouring galaxies toward it at roughly 600 kilometers per second. A cosmic undertow so powerful that it dominates local group dynamics, despite being largely hidden behind the obscuring dust and stars of our own galaxy's disk, the zone of avoidance. For decades, astronomers knew something massive lurked there because of the way galaxies move, but they couldn't see it directly. JWST, with its infrared vision that pierces dust like it barely exists, is finally revealing what's been pulling us toward that corner of the universe, and the answer is both satisfying and slightly terrifying in its scale. The Great Attractor was first proposed in the 1970s when astronomers mapping galaxy motions noticed something peculiar. The local group, our gravitational neighbourhood containing the Milky Way, Andromeda, and dozens of smaller galaxies, wasn't moving through space randomly, but was being pulled in a specific direction at high velocity. This wasn't the smooth Hubble expansion carrying galaxies apart. This was peculiar motion, deviation from the expansion flow caused by the gravitational influence of nearby mass concentrations. By measuring the redshifts and distances of hundreds of galaxies, researchers triangulated the source of this pull to a region roughly 220 million light-years away. But whenever they pointed telescopes at that location, they saw almost nothing. Just a handful of dim galaxies and lots of obscuring material. The problem is that the Great Attractor sits almost directly behind the plane of the Milky Way's disk, a region astronomers call the zone of avoidance. From our perspective embedded in the galactic disk, looking toward the Great Attractor means peering through hundreds of light-years of stars, gas, and especially dust. Tiny solid particles that absorb and scatter visible and ultraviolet light with ruthless efficiency. It's like trying to see across a smoke-filled room. Anything more than a few meters away disappears into haze. Optical telescopes are essentially blind in the zone of avoidance, detecting only the brightest nearby stars and missing the distant universe entirely. Infrared astronomy, pioneered by instruments like the Spitzer Space Telescope and now perfected by JWST, changes the game because infrared light passes through dust relatively unimpeded. Dust grains that block visible light are transparent to longer infrared wavelengths, allowing JWST to peer through the zone of avoidance and map what lies beyond. And what lies beyond, it turns out, is a gravitational monster, not a single compact structure, but a vast supercluster of galaxy clusters, a concentration of mass spanning 300 to 500 million light-years across, containing tens of thousands of galaxies and trillions upon trillions of solar masses, enough gravitational pull to yank our local group and everything around us toward it at substantial velocity. Mainstream astronomy now understands the Great Attractor as part of an even larger structure called the Laniakea supercluster, from the Hawaiian words meaning immeasurable heaven, which encompasses the Great Attractor, the Virgo supercluster, which includes the Milky Way, and several other major concentrations of galaxies, all connected by filaments in the cosmic web. Laniakea contains about 100,000 large galaxies spread across 500 million light-years, and the motions of all these galaxies are governed by the collective gravitational pull of the entire structure. The Great Attractor is one of the densest nodes within Laniakea, but not the only one. There's an even larger structure beyond called the Shapley supercluster, and the entire Laniakea system is slowly falling towards Shapley in a gravitational cascade spanning cosmological distances. Here's a quirky detail that illustrates the scale. At our current velocity of 600 kilometers per second toward the Great Attractor, it would still take us roughly 100 billion years to actually reach it, longer than the universe's current age by a factor of 7. But we'll never make the journey because the expansion of space between us and the Great Attractor is accelerating due to dark energy, and eventually that acceleration will overcome the gravitational pull, carrying us away faster than we're falling toward it. We're caught in a tug-of-war between gravity and dark energy will win, meaning the Great Attractor will gradually recede beyond our cosmic horizon, forever pulling us toward it but never able to reel us in. JWST's infrared surveys are mapping the zone of avoidance with unprecedented clarity, cataloguing thousands of previously hidden galaxies, measuring their distances and velocities, constructing a three-dimensional map of the mass distribution causing our peculiar motion. Early results confirm that the Great Attractor is indeed a massive supercluster, but also reveal unexpected complexity. The mass isn't distributed uniformly but concentrated in several distinct cores, separated by relatively empty voids, creating a lumpy gravitational landscape. This lumpiness affects exactly how galaxies fall toward the structure. Some are accelerating more rapidly than others depending on their position relative to the densest cores, and modelling these motions constrains estimates of the dark matter distribution, which dominates the mass budget and therefore the gravitational dynamics. Scholars still argue about whether the term Great Attractor should refer to the specific overdensity originally identified, or to the broader region including all the major mass concentrations pulling us. Some researchers prefer abandoning the term altogether in favour of Laniakea supercluster core. But nomenclature debates aside, the physical reality is clear. Our local group is falling through space under the gravitational influence of immense mass concentrations hundreds of millions of light-years away, and that motion tells us about the universe's matter distribution on the largest scales. There's also a philosophical angle worth pondering. We're not at rest in the universe. The Earth orbits the Sun at 30 kilometers per second. The Sun orbits the Milky Way's centre at 220 kilometers per second. The Milky Way falls toward Andromeda at 110 kilometers per second. The local group falls toward the Virgo cluster at 300 kilometers per second, and the entire assembly plunges toward the Great Attractor at 600 kilometers per second. Stack all these motions together, and we're hurtling through space at over 1,000 kilometers per second, relative to the cosmic microwave background's rest frame, the closest thing cosmology has to an absolute reference frame. Every second we travel more than 3 times the distance from New York to Los Angeles, carried along by nested layers of gravitational attraction, and we never feel it because everything around us moves with us, like passengers on a smooth train. JWST's revelation of the Great Attractor's structure is both answer and prologue. It answers the decades-old question of what's pulling us and why we can't see it clearly. Massive supercluster hidden behind dust. Mystery solved. But it also introduces new questions. How did such a large structure form? Why is the mass distributed in the particular lumpy configuration we observe? What does the detailed architecture of the Great Attractor teach us about the cosmic web's formation and the interplay between dark matter, ordinary matter, and dark energy on supercluster scales? The gravitational monster has been unveiled, but understanding how it grew to such scale and exactly how it influences the motion of every galaxy within hundreds of millions of light years requires ongoing observation and simulation. You pull your blanket tighter, feeling infinitesimally small as you contemplate falling through space at 600 kilometers per second toward a mass concentration you'll never reach, tugged by gravity's patient hand across distances so vast that light takes 220 million years to traverse them. The Great Attractor pulls, dark energy pushes, and we're suspended between these forces, riding the expansion of space while simultaneously falling through it, participants in a cosmic dance choreographed by gravity and geometry, on scales that dwarf human comprehension. The universe has currents, and we're swept along whether we notice or not, racing through the dark toward unseen shores we'll never reach. You're suspended in the cosmic cycle now, floating through epochs of destruction and rebirth, and here's where JWST reveals something both melancholic and beautiful. Galaxies die and are reborn, their matter recycled through mechanisms so vast and slow that entire civilizations could rise and fall between a galaxy's death throes and its resurrection. The universe practices cosmic composting on the grandest scale, with JWST capturing this process in real time. Watching gas expelled from dying galaxies drift through intergalactic space, cool over millions of years, then rain back down onto the same or neighbouring galaxies to spark new generations of stars. It's the universe's matter conservation system laid bare, proof that nothing is truly wasted in the cosmos, that death and rebirth are built into the fabric of galactic evolution, and the images are hauntingly gorgeous in their clarity. The story of galactic death begins with star formation feedback, the process by which stars ironically kill the very mechanism that created them. When massive stars form, they blast their surroundings with intense ultraviolet radiation and powerful stellar winds that heat and push away nearby gas clouds. When they die as supernovae, they inject enormous energy into the interstellar medium, creating expanding bubbles of hot gas that sweep up surrounding material. This is stellar feedback, and in small doses it regulates star formation, preventing gas clouds from collapsing too efficiently. But in large doses, when many massive stars form simultaneously in a starburst episode, feedback can become catastrophic, heating the galaxy's gas to millions of degrees and driving it outward in galaxy-scale winds that escape the gravitational well entirely, leaving the galaxy gas-poor and unable to form new stars. Mainstream astrophysics has understood this feedback mechanism for decades, but observing it directly has been challenging because the expelled gas is diffuse, hot, and often transparent to optical wavelengths. JWST's infrared and ultraviolet capabilities allow it to trace outflows through multiple techniques, detecting the infrared glow of warm dust entrained in the winds, observing absorption lines where the outflowing gas blocks background light, and mapping ionized gas through emission lines. The results show that galactic winds are ubiquitous, especially in young, actively star-forming galaxies at high redshift where star formation rates are extreme. Gas is expelled at velocities of 500 to 2,000 kilometers per second, fast enough to escape most galaxies' gravity and travel hundreds of thousands of light years into intergalactic space. But here's the beautiful part. The gas doesn't vanish forever. Once expelled beyond the galaxy's gravitational influence, it slows, cools, and eventually stalls as it interacts with the surrounding intergalactic medium and the dark matter halo's extended gravitational field. Over tens to hundreds of millions of years, the ejected material forms vast reservoirs of cool gas in the galaxy's halo, massive clouds containing billions of solar masses slowly raining back down onto the galactic disk like cosmic precipitation. This accretion replenishes the galaxy's gas supply, allowing new rounds of star formation, which eventually triggers new feedback episodes, which ejects more gas, which eventually accretes again. It's a cycle, a galactic heartbeat measured in hundreds of millions of years, each pulse pumping material between the disk and the halo, between star formation and quiescence, between life and dormancy. JWST is imaging this cycle at multiple stages simultaneously by observing galaxies at different redshifts, essentially capturing snapshots of galaxies at different ages. Some galaxies show active outflows, bright, fast-moving shells of ionized gas being violently expelled. Others show extended halos of cool gas surrounding the galactic disk, the rain accumulating in clouds. Still others are caught in the act of accretion, with streams of gas falling inward along filaments, funneled by the cosmic web structure directly onto the galaxy, where it will ignite new star formation. It's like watching a time-lapse of a fountain, seeing water shoot upward, arc through the air and fall back into the basin, except each frame is a different fountain, and the cycle takes hundreds of millions of years per iteration. There's a quirky observational detail that makes this especially compelling. Some galaxies show chemical gradients in their halos, with the innermost regions enriched with heavy elements from previous generations of stars, while the outermost regions remain relatively pristine, containing gas that's been cycling between the galaxy and intergalactic space multiple times. By analysing these gradients, measuring oxygen, carbon, nitrogen abundances at different distances, astronomers can reconstruct the galaxy's history, determining how many cycles of ejection and accretion it's experienced, how efficiently it's retained metals versus mixing them into the broader halo, and how its star formation history correlates with gas flows. It's galactic archaeology through chemistry, reading the periodic table as a historical record. Scholars still argue about the quantitative details of the cycle. How much gas actually escapes versus gets retained in the halo? What fraction of accreted gas is recycled, previously ejected by the same galaxy, versus fresh, primordial gas from the cosmic web? How long does the typical ejection accretion cycle take, and does it vary with galaxy mass and environment? Simulations produce different answers depending on how they model feedback, the energy injected by supernovae and stellar winds, the magnetic fields that can channel or disrupt flows, the role of supermassive black hole feedback in massive galaxies. JWST's observations are now constraining these models with real data, showing which simulations match reality and which need adjustment. Then there's the broader cosmological implication. This recycling process regulates the efficiency of star formation across cosmic history. Without feedback and gas cycling, galaxies would convert all their gas into stars within 1 billion years or so, then sit dormant forever as red and dead ellipticals. Instead, the majority of galaxies remain alive, forming stars at modest rates sustained by the slow drip of accreted gas, replenishing what star formation consumes. The universe's star formation rate peaked around 10 billion years ago and has been declining since, but it hasn't dropped to zero precisely because recycling maintains a trickle of fuel for ongoing star formation. The cosmos is winding down gradually rather than abruptly, aging gracefully into a future where star formation becomes increasingly rare, but never quite stops, at least not for trillions of years. There's also the poetic angle, which astronomers rarely discuss but which permeates the science. The atoms in your body were forged in stars that lived and died billions of years ago, expelled into space through supernovae and stellar winds, cycled through the interstellar medium, accreted onto the gas cloud that formed our sun and solar system, and eventually incorporated into planets and life. You're made of recycled stardust, atoms that have been through multiple cycles of galactic life and death, and someday, billions of years from now, those atoms will be expelled again when the sun dies, dispersed into space, and perhaps incorporated into new stars and planets in future generations. The cosmic recycling system includes us, connects us to the deep past and distant future, makes us participants in the universe's matter conservation across timescales so vast they make human history vanish into insignificance. You settle deeper into sleep's embrace, your consciousness fading like gas cooling in a galactic halo, and you imagine the Milky Way breathing, gas expelled in violent winds, returning in gentle rain, each cycle mixing and enriching the material, ensuring that nothing is lost, that every atom contributes to multiple generations of cosmic structure. Galaxies die, but they don't disappear. They pause, dormant, until accretion rekindles them, and the process will continue, for as long as gravity and thermodynamics govern the universe's evolution. Death is just intermission in the cosmic play, and JWST is showing us the script for every act. You're floating among distant worlds now, your mind drifting across light years to planets orbiting alien stars, and here's where JWST is rewriting the census of habitable environments. Exoplanet atmospheres, those thin envelopes of gas wrapped around worlds hundreds or thousands of light years away, are speaking volumes through their chemical signatures, and what they're saying is extraordinary. JWST's spectroscopic capabilities, splitting starlight that's passed through these atmospheres into wavelengths precise enough to identify individual molecules, are revealing that the conditions suitable for life, the chemical ingredients and energy sources that biology requires, exist on billions more planets than we suspected. The universe isn't just big, it's teeming with potentially habitable real estate, and we're only beginning to catalogue it. The exoplanet revolution began in 1995 when Michel Mayor and Didier Queloz discovered the first planet orbiting a Sun-like star, 51 Pegasi b, a discovery that earned them the 2019 Nobel Prize in Physics. Since then, NASA's Kepler mission and other surveys have catalogued over 5,000 confirmed exoplanets, with statistical analyses suggesting that nearly every star in the Milky Way hosts at least one planet. That's 100 billion to 400 billion planets in our galaxy alone, and a staggering number of those, perhaps 20 to 50 billion, orbit within their star's habitable zone, the Goldilocks region where temperatures permit liquid water on a planet's surface. But discovering planets and understanding their atmospheric chemistry are vastly different challenges, and until JWST, our atmospheric characterization capabilities were limited to the largest, hottest planets. Gas giants orbiting close to their stars, nothing remotely Earth-like. JWST changes everything because its infrared sensitivity and spectroscopic precision allow detailed atmospheric studies of smaller, cooler planets, including super-Earths and mini-Neptunes in or near habitable zones. The technique is transmission spectroscopy. When a planet transits across its star's disk from our perspective, a tiny fraction of starlight passes through the planet's atmosphere before reaching us. Molecules in that atmosphere absorb specific wavelengths, leaving dark absorption lines in the spectrum. By comparing the star's spectrum during transit to its spectrum when the planet isn't blocking it, astronomers isolate the atmospheric signature and identify what molecules are present. Water vapor, methane, carbon dioxide, ammonia, even more exotic compounds like sulfur dioxide or phosphine. The mainstream scientific goal is detecting biosignatures, chemical combinations that strongly suggest biological processes. On Earth, oxygen makes up 21% of the atmosphere, maintained at that level by photosynthetic life. Without biology constantly replenishing it, oxygen would react with surface rocks and disappear within millions of years. Finding oxygen plus methane in an exoplanet atmosphere would be compelling evidence for life, because methane and oxygen destroy each other rapidly, so their coexistence implies continuous production, likely biological. Other potential biosignatures include dimethyl sulfide, produced by ocean phytoplankton on Earth, certain ratios of nitrogen compounds, or even artificial molecules like chlorofluorocarbons if an advanced civilization is inadvertently polluting its atmosphere the way we did for decades. JWST's early exoplanet observations have already produced remarkable results. The planet K2-18b, a super-Earth orbiting a red dwarf star 120 light-years away, shows strong signatures of water vapour and methane, with tentative hints of dimethyl sulfide, though the DMS detection is disputed and requires confirmation. The planet's mass and density suggest it might be a Hycean world, a category of potentially habitable planets with hydrogen-rich atmospheres over global oceans, conditions radically different from Earth, but possibly suitable for exotic forms of life. If confirmed, it would be the first detection of a potential biosignature gas on a habitable zone planet, a discovery of immense significance. Here's a quirky detail that illustrates how complex atmospheric interpretation is. Molecules can be produced by multiple processes, both biological and geological. Methane on Earth comes largely from biology, bacteria in wetlands, termites, livestock. But it's also produced by geological processes like hydrothermal activity. Venus has phosphine in its atmosphere, and when that was announced in 2020, it sparked controversy about whether it indicated aerial microbial life in Venus's clouds, though most researchers now think geological or photochemical processes are more likely explanations. The challenge with exoplanets is that we can't send probes to check. We have only the spectrum, and we must infer the planet's geology, climate, and potential biology from those wavelengths alone, always aware that multiple interpretations might fit the data. JWST's expanding catalogue of atmospheric characterizations is revealing diversity that constantly surprises. Some planets have clouds made of silicate minerals, literal rock vapour condensing into mineral droplets and raining molten glass. Others show extreme temperature variations between day and night sides, or winds circling the planet at supersonic speeds, or atmospheres being stripped away by stellar radiation. And crucially, among this diversity, a growing number of planets show conditions that aren't hostile. Temperatures in the right range, water vapour detected, atmospheric pressures that could support liquid surfaces. The habitable zone isn't a narrow stripe. It's broader and more forgiving than early models suggested, and planets within it are common, not rare. Scholars still argue about what habitable actually means. The traditional definition focuses on liquid water, assuming life requires it as a solvent for chemistry. But could life use other solvents? Liquid methane at cryogenic temperatures on worlds like Saturn's moon Titan, or supercritical carbon dioxide or ammonia water mixtures? Could silicon-based biochemistry substitute for carbon? These are speculative questions, but they matter when interpreting JWST's data. If we search only for Earth-like conditions, we might miss exotic biospheres thriving in environments we dismiss as uninhabitable. Some researchers advocate for a broader definition focusing on energy sources and chemical disequilibrium rather than water alone, casting a wider net that increases the number of potentially habitable worlds. The statistical implications are staggering. If even 1% of planets in habitable zones develop life, and if JWST's observations confirm that habitable zones are abundant around the universe's 200 billion trillion stars, then we're looking at billions of trillions of worlds hosting biology. And if even a tiny fraction of those develop intelligence and technology, the universe should be buzzing with civilizations. This is the Fermi paradox sharpened to a razor's edge. If habitable worlds are everywhere, where is everybody? JWST's discoveries make the silence more puzzling, not less, suggesting either that life is rarer than planetary habitability implies, or intelligence is a rare evolutionary outcome, or civilizations self-destruct, or they're hiding, or the universe is so vast that even abundant civilizations remain isolated by sheer distance. There's also the fringe speculation, gaining slightly more respectability as data accumulates, that some exoplanets might show technosignatures, evidence of advanced civilizations modifying their worlds. Industrial pollution in atmospheres, artificial illumination on night sides, megastructures partially blocking starlight, all could potentially be detected by JWST or future instruments. No credible candidates have been found yet, but the capability exists, and the search is transitioning from fringe to legitimate scientific inquiry, with peer-reviewed papers proposing specific observational strategies. You nestle deeper, you're breathing slow and even, contemplating thousands of worlds scattered across the galaxy, some barren and hostile, others wrapped in life-sustaining atmospheres, perhaps a few hosting oceans and continents and ecosystems, maybe even intelligence pondering the same questions we are, looking at their night sky and wondering if they're alone. JWST is revealing that the universe provides the stage for biology on countless worlds, and while we haven't yet confirmed life beyond Earth, the sheer abundance of potentially habitable environments makes it seem increasingly implausible that we're the only ones, the singular cosmic accident, alone in the vast dark. The chemical signatures say the universe is ready for life, offering billions of chances for chemistry to kindle into biology, and somewhere among those billions, it seems almost inevitable that others have already succeeded. You're drifting through the cosmic microwave background now, that faint afterglow of the Big Bang that permeates all of space, and there's something strange embedded in its pattern, an anomaly that's puzzled cosmologists for 2 decades, and which JWST might finally be helping to explain. The cold spot, a region roughly 70 degrees across in the constellation Eridanus, where the cosmic microwave background is about 70 microkelvins colder than the surrounding sky. It sounds trivial, barely a whisper of temperature difference, but in the exquisitely uniform cosmic microwave background where fluctuations are measured in millionths of a degree, this cold spot is a glaring statistical anomaly, occurring with a probability so low, less than 1% by most calculations, that it demands explanation. And JWST's observations of a vast cosmic void in that direction are providing the most compelling answer yet. We're looking through an enormous underdense region of space, a supervoid perhaps 1 billion light-years across, and its gravitational deficit is leaving a detectable imprint on the ancient light passing through it. The cosmic microwave background, often abbreviated CMB, is the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, making space transparent for the first time. Before that moment, the universe was opaque, a hot plasma where photons constantly scattered off free electrons. Afterward, photons could travel freely, and they've been travelling ever since, their wavelengths stretched by cosmic expansion from visible light into microwaves, arriving at Earth from every direction, with a nearly uniform temperature of 2.725 Kelvin, just barely above absolute zero. The CMB's uniformity is remarkable. Variations in temperature across the sky are only about 1 part in 100,000, tiny ripples that represent the density fluctuations that eventually grew into galaxies and clusters. NASA's COBE satellite first mapped the CMB in the early 1990s, winning its principal investigators the Nobel Prize. Its successor, WMAP, produced more detailed maps in the 2000s, and the European Space Agency's Planck mission delivered the most precise measurements from 2009 to 2013. It was in WMAP and Planck data that the cold spot became undeniable. A roughly circular region centered around celestial coordinates, RA 3 hours 15 minutes, DEC minus 19 degrees, significantly colder than statistical models of the CMB predict. Computer simulations generate millions of random CMB skies based on inflation theory, and the cold spot is colder and larger than appears in 99% of simulated skies. It's an outlier, possibly just a statistical fluke. After all, even rare events happen occasionally, but possibly evidence of something unusual. Mainstream explanations initially focused on foreground contamination, maybe dust in our own galaxy, or radio sources, or instrumental artifacts were creating the appearance of a cold spot without it being genuinely cosmological. Extensive analysis ruled these out. The cold spot is real, imprinted in the CMB itself. The next hypothesis invoked cosmic voids. Photons travelling through underdense regions, vast volumes containing fewer galaxies and less matter than average, experience a subtle effect called the integrated Sachs-Wolf effect. As a photon enters a void, it climbs out of a gravitational potential well, losing energy and redshifting, cooling. As it exits the void, it falls into a denser region and blue shifts, warming. If the universe weren't accelerating, these effects would cancel. But because dark energy causes acceleration, the void's gravitational potential actually weakens slightly during the photon's transit, and the exit blue shift doesn't fully compensate for the entry red shift. Net result: photons emerging from voids are slightly colder than they'd otherwise be. The hypothesis requires a truly enormous void, a supervoid containing significantly less matter than average across 1 billion light-years or more, aligned precisely with the cold spot's direction. For years, this remained speculative because mapping large-scale structure behind the cold spot required extensive galaxy surveys at the right distances, and the region's location near the galactic plane made observations challenging. But surveys gradually accumulated data, and in 2015 astronomers announced the discovery of a large void in the cold spot's direction, roughly 1.8 billion light-years away, with a diameter around 1 billion light-years. It's one of the largest voids ever detected, underdense by about 20% relative to the cosmic average. Here's where JWST enters. The telescope's deep infrared surveys are mapping galaxies at unprecedented distances and sensitivities, filling in the three-dimensional structure of the universe in regions previously poorly sampled. JWST observations toward the cold spot are confirming and refining the supervoid's properties, its size, depth, and exact alignment with the CMB anomaly. Early results suggest the void is even larger and more underdense than initial estimates, potentially explaining most or all of the cold spot's temperature deficit through the integrated Sachs-Wolf effect. It's not a complete slam dunk because the effect's magnitude depends sensitively on cosmological parameters like dark energy's properties, but the fit is compelling. Big void in the right place produces cold spot of approximately the right size and temperature. A quirky detail that makes this more interesting: the supervoid isn't completely empty. It contains galaxies and clusters, just fewer than average. Mapping its internal structure reveals smaller voids and filaments within the larger underdensity, a fractal-like hierarchy where the cosmic web's pattern persists even inside the void. This complexity affects exactly how the integrated Sachs-Wolf effect plays out, because photons don't just transit a smooth underdense bubble, they thread through a tangled web of smaller overdensities and voids, accumulating temperature shifts along the way. Simulating this requires tracking photon paths through realistic large-scale structure, computationally expensive work that's only recently become feasible with modern supercomputers. Scholars still argue about whether the supervoid fully explains the cold spot, or if additional factors are needed. Some researchers calculate that even an enormous void can produce at most 50 to 70% of the observed temperature decrement, suggesting either the void is larger or deeper than measured, or multiple voids along the line of sight combine their effects, or the cold spot is partly a statistical fluke superimposed on the void's genuine signal. Others argue that uncertainties in the integrated Sachs-Wolf effect's calculation, which depends on dark energy models and the exact matter distribution, are large enough that the supervoid could explain the entire anomaly within error bars. There's also the fringe speculation, never entirely serious but never entirely dismissed, that the cold spot could indicate something genuinely exotic, a collision with another universe during the inflationary epoch, leaving a bruise in the CMB where the bubbles touched, or a topological defect, a cosmic string or domain wall left over from phase transitions in the early universe, or even, and here we venture into science fiction territory, a region where physical laws differ slightly, perhaps a remnant of how space itself formed. These ideas lack supporting evidence and are mentioned primarily to illustrate how statistically unlikely features can spawn creative theoretical speculation. But the supervoid explanation is mainstream, testable, and increasingly well supported by data. JWST's contribution is nailing down the void's properties with sufficient precision to test quantitative predictions. If the integrated Sachs-Wolf effect from the observed void matches the cold spot's temperature decrement within uncertainties, the mystery is solved, and the anomaly becomes another example of large-scale structure affecting the CMB in predictable ways. If discrepancies remain, then either our understanding of voids and the Sachs-Wolf effect needs refinement, or the cold spot has additional causes, or we've stumbled onto something genuinely anomalous that current cosmology can't explain. You shift slightly, pulling your covers closer, and you imagine the cold spot as a cosmic shadow, cast not by something blocking light, but by an absence, a vast region of space where matter chose not to congregate, a billion light-year bubble of relative emptiness through which ancient photons passed, emerging slightly cooler, their temperature carrying information about the void's existence across 13 billion years until detected by satellites orbiting Earth. JWST is mapping the shadow's source, revealing the void's depth and structure, turning a cosmological mystery into a solved problem, one more piece of the universe's puzzle clicking into place. The universe contains voids so large they chill the light of creation, and we're finally seeing them clearly enough to understand why. You're suspended in the river of time itself now, your consciousness stretched between moments. And here's where JWST captures something Einstein predicted, but which still feels like sorcery when you see it directly. Time dilation, the slowing of time in strong gravitational fields or at high velocities, observed across cosmological distances by watching supernovae explode in apparent slow motion. They're like curves stretched and distorted as relativity warps the flow of time itself. It's one thing to read about time dilation in textbooks, to understand it as mathematical consequence of special and general relativity. It's another entirely to watch it happen, to see a distant star's death throes unfolding at half speed or quarter speed, because the universe's expansion has stretched not just the wavelengths of light, but the intervals between photons, the ticking of cosmic clocks, time itself dilated across billions of light years. Einstein's special theory of relativity, published in 1905, established that time passes differently for observers in relative motion. A clock moving at high velocity runs slower relative to a stationary clock, not because of mechanical malfunction, but because time itself flows differently in different reference frames, a consequence of space-time's geometry and the constancy of a light's speed. His general theory of relativity, completed in 1915, extended this to gravity. Time passes slower in stronger gravitational fields, so a clock on Earth's surface runs slightly slower than one in orbit, and a clock near a black hole's event horizon nearly stops relative to distant observers. These aren't illusions or measurement artifacts. Time genuinely flows at different rates depending on motion and gravity, a feature of reality so counterintuitive that it took Einstein's genius to recognize it, and decades of experimental verification to convince skeptics. Cosmological time dilation is related but distinct. It emerges from the expansion of space itself. When we observe a distant galaxy at redshift z, we're seeing it as it was billions of years ago, when the universe was smaller and younger. But we're not just seeing old light. We're seeing events unfold at a rate that's slower than they occurred in the galaxy's own reference frame, stretched by the expansion that happened between emission and observation. For a galaxy at redshift z equals 1, events appear to occur at half speed. At z equals 2, 1/3 speed. This affects anything time-dependent: the duration of supernova explosions, the oscillation periods of variable stars, the decay rates of radioactive elements, everything stretched in proportion to the expansion factor. Type 1. A supernovae provide the perfect test case because they're both bright enough to see across billions of light years and well understood enough that their intrinsic time evolution is calibrated. These are exploding white dwarf stars that reach a critical mass, ignite runaway nuclear fusion, and detonate completely, releasing energy comparable to an entire galaxy for a few weeks. The light curve, brightness over time, follows a characteristic pattern: rapid rise to peak brightness over about 3 weeks, then gradual decline over months, with specific timescales determined by the physics of the explosion and the radioactive decay of nickel-56 into cobalt-56 into iron-56. Astronomers have observed thousands of nearby Type 1a supernovae, establishing their typical light curve duration with precision. When JWST observes Type 1 a supernovae at high redshift, z equals 1, z equals 2, even approaching z equals 3, the light curves are stretched exactly as relativity predicts. A supernova that would reach peak brightness in 3 weeks in its own rest frame appears to take 6 weeks at z equals 1, 9 weeks at z equals 2, proportionally longer at higher redshifts. The entire explosion is filmed in slow motion, each phase extended by the expansion factor. This was first convincingly demonstrated in the late 1990s by the same surveys that discovered cosmic acceleration, and it remains one of the cleanest confirmations of general relativity on cosmological scales. JWST's superior sensitivity allows detection of these supernovae at even greater distances and fainter brightnesses, extending the time dilation measurements to earlier cosmic epochs. Here's the mainstream scientific significance. Time dilation measurements confirm that redshift is genuinely cosmological, caused by expanding space-stretching wavelengths, rather than caused by some alternative mechanism like tired light theories, where photons somehow lose energy during their journey. Tired light can't explain time dilation. Only genuine cosmological expansion predicts that observed durations stretch in lockstep with wavelengths. The observations match general relativity's predictions to within a few percent across redshifts spanning most of cosmic history, an extraordinarily stringent test of the theory's validity at scales millions of times larger than the solar system where it was first tested. A quirky detail that illustrates the precision. Astronomers can measure time dilation not just in supernovae, but in quasar variability. Quasars, supermassive black holes actively accreting gas, flicker and vary in brightness, on timescales from hours to years, as turbulent processes in their accretion disks produce changes in light output. When you observe quasars at different redshifts and measure how quickly they vary, the high redshift ones vary more slowly by exactly the factor predicted by cosmological time dilation. This was tricky to demonstrate because quasars are inherently chaotic, each with different intrinsic variability patterns, but statistical analyses of thousands of quasars show the pattern clearly. Higher redshift equals slower variability, with the expansion factor stretching time. Scholars still use time dilation measurements to test refined predictions of general relativity and to constrain alternative theories of gravity. Some modified gravity theories, proposed to explain cosmic acceleration without dark energy, predict subtle deviations from general relativity's time dilation formula at high redshifts or in specific density environments. JWST's observations are precise enough to test these predictions, and so far Einstein's original formulation remains undefeated. No statistically significant deviations have been found, tightening the constraints on alternative theories and reinforcing general relativity as the correct description of gravity across cosmological scales. There's also a philosophical dimension worth contemplating. Time dilation means the universe doesn't have a single universal now. Events simultaneous in one reference frame aren't simultaneous in another. A supernova we observe today, happening 10 billion light-years away, occurred in our past according to our clocks, but an observer moving rapidly relative to us might calculate that it's happening in their present or even their future depending on their velocity and direction. The universe's now is observer-dependent, sliced differently by different reference frames, making the flow of time fundamentally relative rather than absolute. There's no cosmic clock ticking uniformly everywhere. Time is local, personal, woven into space-time's fabric in ways that depend on motion and gravity. JWST captures this relativity visually, freezing distant explosions in extended slow motion, each frame stretched by the expansion that occurred while light travelled toward us. When you see those stretched light curves, supernovae taking months where they should take weeks, you're seeing time itself dilated, watching the universe's expansion rate written directly into the duration of events, proof that space-time isn't a static stage but a dynamic, expanding fabric that stretches not just space but the intervals between moments, the flow of time, the rate at which cosmic processes unfold. You nestle deeper into your pillow, your own perception of time growing fuzzy as sleep approaches, and you ponder the strangeness that time passes differently across the universe, that distant galaxies experience time at rates different from ours, that the very concept of now dissolves into relativity when you consider cosmic scales. Einstein saw this through pure thought, mathematical insight revealing features of reality invisible to intuition, and now JWST makes it visible, turning abstract equations into observable phenomena, confirming that the universe is even stranger than our everyday experience suggests. Time dilates, stretches, flows at different rates depending on where you are and how fast you're moving, and JWST watches it happen across billions of light years, one slow-motion supernova at a time. You're hovering at the boundary between the real and the simulated now, your mind drifting through quantum fog, and here's where JWST's observations brush against one of the strangest philosophical questions in modern physics. Are we living in a simulation, a computational model running on some substrate beyond our comprehension, and could certain patterns in JWST's deepest images, subtle pixelation-like effects, unexpected regularities at the smallest observable scales, peculiar correlations that hint at underlying discrete structure, provide evidence that reality has a fundamental graininess consistent with information processing, rather than continuous mathematics? It sounds like science fiction, the kind of idea that belongs in late-night dorm room discussions rather than peer-reviewed journals. But the simulation hypothesis has gained surprising traction among serious physicists and philosophers, and JWST's unprecedented resolution is probing scales where, if we're living in a computational universe, the pixels might start showing. The simulation hypothesis was popularized by philosopher Nick Bostrom in his 2003 paper, Are You Living in a Computer Simulation?, which presented a probabilistic argument. If civilizations commonly survive to develop computational capabilities sufficient to simulate conscious beings and their environments, and if they choose to run many such simulations, for research, entertainment, or other purposes, then simulated consciousnesses would vastly outnumber real ones, making it statistically likely that any given conscious entity, including us, exists within a simulation rather than in base reality. The argument is rigorous within its assumptions, though those assumptions are debatable. Maybe most civilizations self-destruct before reaching simulation capabilities, or maybe running ancestor simulations is prohibited or uninteresting to advanced civilizations. But if the premises hold, the conclusion is provocatively hard to dismiss. Mainstream physics approaches this differently, focusing not on the philosophical question of whether we're simulated, but on whether space-time has discrete structure at the smallest scales. Quantum mechanics and general relativity, our two foundational theories, are incompatible in extreme conditions, near black hole singularities or at the Big Bang. because quantum mechanics assumes space-time is a smooth background, while general relativity treats space-time as dynamic and curved. Most approaches to quantum gravity, string theory, loop quantum gravity, causal set theory, predict that space-time becomes discrete or quantized at scales near the Planck length, about 10 to the power of negative 35 meters, far smaller than anything directly observable. But if space-time is fundamentally discrete, built from finite information, it shares a formal similarity with computational models where continuous variables are approximated by discrete states. Not a simulation necessarily, but structure that could support simulation. JWST's deep field images, particularly when processed at extreme magnifications and analysed for statistical patterns, show some features that have sparked discussion. In certain observations of the most distant galaxies, researchers have noted subtle regularities in how light intensity varies at the smallest angular scales. Not random noise as expected from photon statistics and instrumental effects, but patterns with weak periodicities or correlations that some interpret as hints of underlying discrete structure. These patterns are at the very edge of detectability, statistically marginal, and most astronomers attribute them to instrumental artifacts, atmospheric effects. Even for space telescopes, scattered light from the solar system introduces noise, or simple pareidolia, the human tendency to see patterns in randomness. But a small minority of researchers take them seriously as potential signatures of space-time discreteness. If space has a minimum quantum of length, a fundamental pixel size below which smaller has no meaning, then observations across vast distances might accumulate subtle effects that manifest as periodic patterns or unexpected correlations at specific scales. It's analogous to how digital images show aliasing artifacts when you zoom far enough to see individual pixels. The universe, if discrete at the Planck scale, shouldn't show obvious pixelation at observable scales, because the Planck length is incomprehensibly tiny. You could fit more Planck lengths across an atomic nucleus than you could fit atoms across the observable universe. But cumulative effects across billions of light years, combined with quantum interference and gravitational lensing, might amplify Planck-scale discreteness into detectable patterns. Here's a quirky detail. Some quantum gravity theories predict specific observational signatures that JWST and other instruments can test. Loop quantum gravity, for instance, predicts that the speed of light might vary very slightly with wavelength if space-time is fundamentally discrete, an effect called quantum gravity-induced dispersion. High-energy photons would travel infinitesimally slower than low-energy ones, and over billions of light-years this could introduce detectable time delays. Gamma-ray bursts, intense flashes of high-energy light from distant cosmic explosions, provide test cases because they emit photons across a wide energy range simultaneously. Observations have so far found no evidence of energy-dependent speed variations, placing tight constraints on some quantum gravity models, but the search continues with increasing precision. Scholars still argue fiercely about whether the simulation hypothesis is science or philosophy. Critics point out that it's unfalsifiable in principle. Any observation inconsistent with a simulation could be explained as the simulators choosing to make it appear that way, or limitations in our simulated understanding preventing recognition of the simulation. Proponents counter that specific simulation architectures would produce detectable artifacts. Computational resource limits might manifest as maximum speeds, light speed, minimum scales, Planck length, or regularities in physical constants that reflect the simulation's coding choices. Testing these predictions is legitimate science even if the broader hypothesis remains philosophical. There's also the information theoretic angle. Some physicists influenced by black hole thermodynamics and the holographic principle argue that the universe is fundamentally made of information rather than matter, and energy being primary. John Wheeler's famous phrase, "it from bit," captures this. Every physical quantity, every it, derives from binary information, from bits. If reality is informational at its core, then distinguishing between a universe that's real but informational and one that's a simulation processing information becomes semantically murky. Both descriptions might be equivalent ways of talking about the same underlying structure. JWST's role in this discussion is providing the highest resolution observational data of distant structures, allowing tests of space-time's properties at extreme scales. No definitive evidence for discreteness or simulation artifacts has emerged. The universe looks continuous and consistent with standard physics within observational uncertainties, but the capability to test these ideas, to search for patterns that would indicate underlying computational structure, represents a fascinating convergence of cosmology and fundamental physics with philosophical questions about reality's nature. You sink deeper into sleep's gentle grasp, the boundary between your dreaming mind and waking reality blurring in ways that feel suddenly relevant. If we're simulated, would we know? Could we know? If the simulation is sufficiently detailed and self-consistent, probably not. We just experience it as reality, which is functionally equivalent to it being real. And if space-time is discrete at the deepest level, does that make it less real, or just different from the continuous mathematics we use to approximate it? The questions spiral inward, each answer raising new questions, and somewhere JWST floats in orbit, capturing photons that travelled billions of years through space that might be continuous, or might be discrete, real, or simulated. And either way, the photons encode information about galaxies and stars and the universe's structure. And that information is what matters. The patterns and relationships, independent of the substrate supporting them. Reality's deepest pixels, if they exist, remain hidden. But JWST is looking, measuring, testing, probing the boundaries where observation meets interpretation, where physics brushes against philosophy. You're drifting at the edge of everything now, consciousness dissolving into the space between thoughts. And here's where JWST's observations reach toward the most profound cosmological mystery. What happened at the very beginning, and what lies beyond the boundary of our observable universe? The telescope is detecting asymmetries in the distribution of galaxies at extreme distances, subtle patterns where the universe looks slightly different in one direction than another. And these deviations from perfect uniformity hint at something extraordinary. The possibility that our universe collided with another during the inflationary epoch, that we're seeing evidence of a cosmic crash billions of years ago, when our bubble universe scraped against or merged with a neighbouring bubble, leaving scars in the large-scale structure that JWST is now sensitive enough to detect. It's speculative, living on the edge of testable science. But the data is compelling enough that serious cosmologists are developing models and predictions to test whether we've stumbled onto the first observational evidence of other universes. The story begins with inflation, that brief period of exponential expansion in the universe's first fraction of a second. The inflationary paradigm solves multiple cosmological problems: the horizon problem, the flatness problem, the monopole problem, and it naturally produces the density fluctuations that seeded galaxy formation. But inflation doesn't predict a perfectly uniform universe. Quantum fluctuations during inflation get amplified to cosmic scales, creating a random pattern of slightly overdense and underdense regions. These fluctuations should be statistically isotropic, meaning they look the same in all directions with no preferred orientation or asymmetry. The universe should be, on average, uniform across the sky once you account for random variations. But JWST's deep surveys, particularly when combined with cosmic microwave background data from Planck, reveal subtle violations of this isotropy. The universe isn't quite uniform. There's a slight hemispherical asymmetry, where one half of the sky shows marginally stronger temperature fluctuations than the other, and there are peculiar alignments of the larger scale structures, what cosmologists call the axis of evil, a somewhat tongue-in-cheek name for the unexpected alignment of the CMB's lowest multipole moments along a particular direction. These features are statistically marginal, hovering around 2 to 3 sigma significance, enough to be intriguing but not definitive. They could be flukes, instrumental artifacts, or foreground contamination from the Milky Way or solar system, or they could be real. If real, one explanation is cosmic collisions during inflation. Eternal inflation predicts that bubble universes nucleate within the inflating background, each bubble expanding and cooling into a universe with its own properties. Most bubbles never interact, separated by vast distances in inflating space. But occasionally two bubbles might collide, their boundaries intersecting during the inflationary epoch. The collision would leave an imprint, a circular temperature pattern in the cosmic microwave background centered on the collision direction, with specific temperature profiles depending on the collision's energy and timing. Multiple collisions could produce overlapping patterns, creating complex asymmetries. Mainstream cosmology treats bubble collisions as highly speculative but not absurd. The mathematics is well defined within eternal inflation frameworks. Researchers have calculated what collision signatures would look like and how to search for them in CMB data. Several candidate features have been identified, circular temperature anomalies that don't obviously fit random fluctuations, but statistical tests have been inconclusive. The problem is that the CMB is a single realization of a random field. You can't run the Big Bang multiple times to see if features repeat. Any specific pattern might be a fluke, and distinguishing genuine collision signatures from random chance requires very strong evidence that hasn't quite materialized yet. JWST adds a new dimension by mapping large-scale structure in 3 dimensions across cosmic time. If a collision occurred, it wouldn't just affect the CMB, it would influence how structure formed in the collision's aftermath, potentially creating directional asymmetries in galaxy distributions that persist across billions of years. Early JWST analyses of galaxy clustering at high redshift show hints of such asymmetries, slightly more structure in certain sky directions, correlations between distant galaxy positions and CMB anomalies. But again, the evidence is marginal, complicated by selection effects and incomplete sky coverage. Here's a quirky detail that makes this more tantalizing. The asymmetries, if real, seem to align with other anomalies. The hemispherical asymmetries axis, the CMB's axis of evil, the direction of the universe's peculiar velocity relative to the CMB rest frame, and some large-scale structure features all point towards similar regions of sky, around the constellation Eridanus, near the cold spot we discussed earlier. This could be coincidence, multiple unrelated effects happening to align, or it could be evidence that something genuinely unusual happened in that direction, a cosmic event whose effects propagated through multiple observables. Collisions, supervoids, or exotic topological features could potentially explain the correlations, but teasing apart these possibilities requires more data and better modelling. Scholars still argue about whether eternal inflation and bubble collisions are science or metaphysics. If other universes are forever beyond observation, can claims about them be scientific? Collision advocates argue that if collisions leave detectable imprints in our observable universe, the hypothesis is testable and therefore scientific, regardless of whether we can directly observe other universes. Critics counter that the models have enough free parameters, collision timing, energy, angle, number of collisions, that they can be adjusted to fit almost any observed pattern, reducing their predictive power and falsifiability. There's also the philosophical vertigo. If our universe collided with another, what happened at the boundary? Did physical laws merge or conflict? Were there regions where different vacuum states coexisted, where particles from one universe interacted with particles from another, under potentially different forces? Did consciousnesses exist in the other universe, and what was their fate? These questions slide from physics into science fiction, but they're not nonsensical. They're genuine inquiries about what happens when domains with different effective physical laws come into contact. Scenarios that quantum field theory and cosmology can address in principle, even if observations remain far out of reach. JWST's contribution is mapping the universe's large-scale structure with unprecedented precision and depth, constraining models of inflation and its consequences. Whether the observed asymmetries are collision signatures, artifacts of foreground contamination, statistical flukes, or evidence of something else entirely remains uncertain. But the capability to test predictions of eternal inflation and bubble collisions represents a remarkable achievement, turning ideas that seemed purely theoretical into observationally accessible hypotheses, bringing the multiverse from philosophy into empirical science, or at least to its doorstep. You pull your blanket closer, feeling the weight of cosmic history pressing down, and you imagine our universe as a bubble floating through a higher dimensional space, brushing against other bubbles, perhaps merging with one billions of years ago in an event so energetic and strange that its echoes persist in the sky's asymmetries, faint scars from a collision at the dawn of time. JWST peers at those scars, measuring their properties, testing whether they match predictions, slowly building the case that we're not just living in a universe, but in a universe that's interacted with others, part of a larger multiverse structure whose existence might be inferable from patterns in our own cosmic backyard. The universe might bear bruises from encounters with its neighbours, and we're finally developing the instruments sensitive enough to see them, to read the story of cosmic collisions in the arrangement of galaxies and the temperature of ancient light. You're floating in the quiet dark, almost asleep now, and we've arrived at the culminating revelation, the synthesis of everything JWST has shown us. What does bigger really mean when we say the universe is way bigger than we thought? The observable universe's radius has just expanded by billions of light years, not because space suddenly inflated, but because our measurements were wrong, our instruments inadequate, our understanding incomplete. JWST has pushed back the frontier, revealing galaxies at distances we couldn't reach before, detecting structures we couldn't see, mapping matter we didn't know existed. The observable universe, that sphere of space from which light has had time to reach us since the Big Bang, is larger than we calculated. But more importantly, the unobservable universe, the vast infinity lying beyond our cosmic horizon, remains humbling in its incomprehensible scale, and JWST's discoveries make that infinity feel more real, more populated, more magnificent than we dared imagine. Let's ground this in numbers that somehow fail to capture the scale. The traditional estimate placed the observable universe's radius at about 46.5 billion light-years in any direction, accounting for the expansion that occurred while light travelled toward us. That's a sphere encompassing roughly 93 billion light-years across, containing an estimated 2 trillion galaxies, each with billions or trillions of stars. JWST's discoveries are revising this upward by detecting galaxies at redshifts beyond Z equals 15, at distances corresponding to light that's been travelling for over 13.4 billion years, and by mapping structure that previous telescopes missed, the effective observable boundary has been pushed outward. The exact numbers are still being calculated as data accumulates, but conservative estimates suggest the observable universe is at least 5 to 10% larger in volume than pre-JWST measurements indicated. Hundreds of billions of additional cubic light-years added to the census, containing hundreds of billions more galaxies that were always there but invisible until now. But here's the profound realization. The observable universe, no matter how large, is almost certainly finite, bounded by the cosmic horizon beyond which light hasn't had time to reach us. The total universe, the full extent of space beyond our horizon, could be infinite, extending forever in all directions with no edge or boundary, just endless galaxies and stars and planets beyond the limits of observation. Inflation theory actually suggests the universe is likely infinite. The exponential expansion stretched space so dramatically that even if the universe began with finite size, it's now far larger than the observable portion, possibly infinite. If space is flat, as observations indicate, and if it extends beyond our horizon as far as physics allows, then bigger doesn't just mean a larger sphere. It means recognizing that what we see is an infinitesimal fraction of what exists. The mainstream cosmological framework accepts this hierarchy of scales. The observable universe is large but finite, determined by light travel time and expansion. The total universe is vastly larger, possibly infinite, forever beyond direct observation, but inferable from the physics governing cosmic evolution. And if eternal inflation and the multiverse are real, then our entire universe, observable and unobservable combined, is just one bubble among infinite others, each potentially infinite itself, creating a hierarchy of infinities that makes the mind real. JWST hasn't proven any of this definitively, but by pushing the observational boundary outward, by revealing that space is more densely packed with galaxies than we thought, by showing that structure extends to the earliest possible epochs, it's made the case for vastness more visceral, more undeniable. There's a curious emotional response to these discoveries, something astronomers rarely discuss in technical papers, but which permeates the field. Confronting the universe's true scale produces a mixture of awe and existential vertigo. You're simultaneously insignificant, a single organism on a single planet orbiting a single star among hundreds of billions in a galaxy that's one of trillions, and precious, because as far as we know, you're one of the rare configurations of matter that's achieved self-awareness, capable of contemplating the cosmos and understanding your place within it. JWST's images capture both feelings: the overwhelming scale that dwarfs human concerns, and the intricate beauty of galaxies and nebulae that speaks to something almost aesthetic. A universe that's not just large but also structured, patterned, filled with forms that evoke wonder. The philosophical implications are unavoidable. If the universe is vastly larger than we thought, containing quintillions of planets as JWST's rogue planet discoveries suggest, and if a significant fraction of those planets are habitable as atmospheric surveys indicate, then the probability that we're alone drops towards zero. The universe isn't just big, it's almost certainly teeming with life, intelligence, perhaps civilizations far older and more advanced than ours. The Fermi paradox, where is everybody, becomes more pressing, not less, because JWST is showing that the universe provides abundant opportunities for biology and intelligence to emerge. Maybe the distances are simply too vast, isolating civilizations in bubbles of space-time they can never escape. Maybe intelligence is self-limiting, civilizations destroying themselves before achieving interstellar communication. Maybe we're among the first or the last. The silence remains, but the stage on which it plays out has been revealed as incomprehensibly larger than we imagined. There's also the temporal dimension. JWST is showing us the universe at its beginning, when it was smaller, denser, hotter. The structures we see at z equals 15 or z equals 20 existed when the universe was only a few 100 million years old, occupying a space that's since expanded 1,000-fold or more. The galaxy's JWST images are long gone in their observed forms, having merged or evolved over billions of years into structures we can't see because their light hasn't reached us yet. We're watching cosmic history unfold in reverse, seeing ancient light from early epochs and extrapolating forward to understand how those seeds grew into the present universe. JWST makes the universe's history tangible, transforming abstract timescales into visual narratives of formation and evolution. You nestle deeper into your pillow, breathing slow and even, and the numbers dissolve into feeling. A sense of floating in an ocean whose depth and extent you'll never fully know, surrounded by currents and life and structure extending beyond every horizon. JWST has shown that the universe is bigger in every sense. More galaxies, more stars, more planets, more structure at earlier times, more matter in unexpected places, more mysteries than we had questions for, and beyond everything we can see lies an unobservable infinity, a realm forever beyond the reach of light, but present nonetheless, part of the same reality, governed by the same physics, filled with galaxies we'll never glimpse and stories we'll never hear. The universe is way bigger than we thought, not just in radius, but in complexity, richness, and possibility. JWST has expanded our cosmic census, pushed back the frontiers of knowledge, and in doing so has reminded us that every answer generates new questions, every discovery reveals deeper mysteries. We know more than we did, and yet we understand less than we thought. A paradox of knowledge that's humbling and thrilling in equal measure. The universe keeps its secrets generously distributed across infinite space and deep time, and we've barely begun to catalogue them, barely scratching the surface of what's out there waiting to be discovered. And now, as the journey through cosmic revelation comes to its gentle close, let your breathing deepen. Let the weight of these vast distances and timescale settle softly around you, like a blanket woven from starlight itself. The universe stretches beyond comprehension, yes, but you're here. A brief configuration of atoms that learn to wonder, to question, to seek understanding across billions of light years. JWST floats in orbit, its golden mirrors capturing ancient photons, and somewhere in the data streams flowing back to Earth are answers to questions we haven't yet learned to ask. Discoveries that will reshape our understanding once again, mysteries that will occupy curious minds for generations to come. The galaxies spin in their slow cosmic dance, stars ignite and fade, planets drift through the dark, and the universe expands into its infinite future, carrying all of this, the known and unknown, the observed and unobservable, the measured and the mysterious, forward through time. You're part of it, connected through physics and chemistry to everything that's ever been. And as sleep finally claims you, you can rest in the knowledge that the universe is bigger, stranger, and more wonderful than anyone suspected, and that's exactly as it should be. Sweet dreams, traveller. The cosmos is vast, but you've journeyed through it tonight, and now it's time to rest. The stars will still be there tomorrow, waiting patiently as they have for billions of years, ready to share more secrets when you're ready to listen again.